All right, well, it is 11 o'clock in the morning Eastern Time. I see we've got some people watching the stream already, so thank you all very much for attending. And we are going to go ahead and kick things off with a welcome to the 8th Annual OpenVSP Workshop in 2020. We are fully virtual and streaming to the OpenVSP Videos YouTube channel. My name's Brandon Litherland, an aerospace engineer at NASA Langley Research Center in the Aeronautic Systems Analysis Branch. So, this is fully virtual this year, so we can adhere to social distancing practices and eliminate the need for travel, which also means that this year there are no fees, there's no registration, everything is free and open distribution to the public. So by all means, feel free to share these links or the workshop page or sessions on social media, within your working groups, among your friends, or to anyone that you think would benefit from these talks. A reminder to our online viewers, please remember to set your player quality to 1080p. YouTube does not do this automatically, so you'll want to click on this little gear button in the bottom corner of your player and set that to 1080p for the best quality. And if you happen to go away and come back to a session later on, you'll need to do this again just in case the quality has reset itself. If you intend to follow along on the tutorials and work in VSP side by side, we do recommend watching the workshop on a separate screen. So if you happen to have a smart device handy, you can use that. If you have a separate screen on your desktop, you can do that as well. And for those of you that are busy or have to go to meetings or have class, for example, please be aware that these sessions are going to be recorded and uploaded for viewing later. A reminder to our presenters, please remember to close the VSP live stream while presenting to avoid any audio feedback issues. And when you're sharing your screen, try and remember to maximize your presentation to get the best resolution. And share the display that's closest to a 16:9 aspect ratio if you're using multiple screens. And that's going to give our online audience the best viewing experience. For joining the Teams meeting to present your screen, only the moderators or the speakers should be on the Teams meeting at any time. So if you're not scheduled to present, please remember to leave the Teams meeting and close that out so that you can rejoin and follow along on the live stream. So a big thank you to all of our presenters that are scheduled for this year. We really appreciate your time and effort in making this a successful workshop. To interact with our speakers and presenters in real time, you can post questions or comments to the NASA Conferences I/O service. The links to the social Q&A are on the main page for the workshop and below each video player. So if you look below your video player right now, there's a blue link that'll take you to the social Q&A. And when that opens up, you simply click the Add Ask button to post a comment or a question. Moderators will either address these questions or comments directly or forward popular topics to the speaker in real time. Please remember that there is a slight delay between the Teams meeting and the streamed content, so the Q&A feed is going to be a little bit behind, but when you post questions, we're going to be able to feed those or answer them. We've got various moderators for this event, and we'll be monitoring that for the duration of the workshop. Also be aware that the question and answer feed is going to be stored for a while so you can go back and review these as needed. And any questions not addressed during the speaker's time can be answered later, so feel free to go back and look at these. A word on our session schedule and the links to those. You can always get information on the workshop main page under the OpenVSP wiki under the Workshop 2020 page. But we have various sessions linked out to each day between 11 a.m. and 2 p.m. and 2 p.m. and 5 p.m. Eastern Time. And the links to these sessions are also included in the YouTube video description underneath the video player. So if you click the Show More button, you'll see this drop down, and all of these links here in blue take you to each of the individual sessions. So for example, when we're done with session 1 today and you want to jump to session 2, simply click on this link. It's going to open up the new player and you'll be set on go. We'll go ahead and take a minute to talk about our technical schedule for the next few days. We're going to start off with an introduction, some of the basics of modeling, and we're going to close things out today with a bit of a discussion about the parasite drag tool. On day 2, we're going to be discussing improvements to VSP and some analyses with a heavy focus on VSP Aero. So in the earlier sessions, we'll be dealing with theory, validation, and features and some basics of the tutorial. After that, we're going to go into some recent additions that have been added over the last year or two, and then an advanced VSP GUI demonstration. We'll be closing out the day with a demonstration of high fidelity modeling and an update from Justin Gravita ES Aero for their SBIR work in improving VSP over the last year or so. On the third day, we'll be discussing tool interaction and developer sessions. So we'll be working between tools like FlightStream and M4 Structure Studio, and we'll be recording a build session where we're going to build OpenVSP from the source code. And we're also going to be presenting how to work with OpenVSP using the API and the MATLAB integration tools. So lots of heavy lifting on that third day, but really interesting stuff, and I highly recommend that you join in and watch that. So I see that there are people already posting to the social Q&A. We really appreciate that. And I want to thank you all for watching. I hope you enjoy it. On the social Q&A, if you're having issues with video quality, audio quality, anything that you're finding is not working quite right on the workshop, please let us know so that we can address those concerns immediately. But with that, I'm going to go ahead and say thank you all again, and I'm going to hand off to Rob McDonald, who's going to introduce OpenVSP.
Thank you much, Brandon, and thank you everybody for joining us. It's great to have participation for this 8th VSP workshop. I'm sorry I can't be in person this time, but we all look forward to next year. For those of you who are new to VSP, VSP is not CAD. We're very clear about that, but it is a geometry tool for design, and that makes it worth spending a little time thinking about what that means. And if you remember back to when you took statics in engineering school, you'll remember that everything you did started with a drawing. And what you'll find is that shape is really a fundamental starting point for any sort of a physics-based engineering analysis. Whether you're going to do arrows, structures, mass properties, signatures, manufacturing, whatever it is, shape is the starting point. And no matter what discipline you're doing and no matter what level of fidelity you're doing, shape is that common denominator. Unfortunately, in practice, there's very little commonality when you go out to make these models and do this kind of analysis. In fact, most geometry is misrepresented by the analyses that we do, and that's okay for the most part. CAD models are typically built with a single intent. You might build one CAD model to represent manufacturing, where the target is CAM and the actual real full shape. You might have another CAD model on an aircraft to represent the integration and maintenance, packaging, accessibility, those things. Another CAD model might represent the structures, and yet another CAD model for the aerodynamics to represent the OML, propulsion, and control surfaces. That's a tremendous duplication of effort and tremendously complicated to keep these separate models. There's also a gap. Historically, engineering analysis tools used to have their own geometry input. You would specify the wingspan and the airfoils and the twist and the chord in an aerodynamics tool, and it would generate its own geometry representation and do the analysis on that. The more modern approach is a CAD-based approach. This really comes from the finite element analysis world, where you start with a general purpose CAD program, and then you use a general purpose grid generation and pre-processing tools that are very generic and don't know anything about the geometry. That only works for certain analyses and for tools that have been developed with that in mind. OpenVSP positions itself in between those. We know about the geometry. We're not a single tool for analysis integrated. You don't have to repeat the geometry description for every tool you use, but OpenVSP can then feed many different tools, and it knows that the model is an airplane. Now, there's also typically in practice a lot of analysis fidelity holes, and there's many reasons why this exists in practice and in industry, but for the most part, an organization will invest tremendous effort in getting a single model to analysis workflow working, and there's huge investments in that, and your fidelity is at least limited, if not chosen, by the geometry model you have, and it's hard to change that fidelity later. And so what this means is that a design engineer ends up choosing the tool, the analysis tool that they're using, not based on what's the right tool for a given job, but by which tool is fully automated and integrated in our workflow? Which tool do I have the most investment in? And then every time you need to use something, you end up using that same tool. And what you end up with is, instead of a densely populated fidelity discipline matrix where you have multiple fidelity choices you can make at every discipline throughout the design process, you've just got one here and there. And due to those sparse choices, you don't get to make the right tool choice independent as you're working. Now, there's many possible representations of a geometry. Again, in CAD, there's just sort of one representation. But there's many ways as engineers we think about the shapes. You might represent a wing as a stack up of its airfoils, or maybe a wireframe, or maybe a smooth surface representation. It might be an unstructured isotropic triangle mesh. It might be a coarse triangle mesh. It might be a thin vortex lattice representation. It could be an FEA model with internal structure, an equivalent plate representation, or an equivalent beam structures representation. And there's many more. Which of these is really the geometry? And what we want to emphasize with VSP is that the shape is really just an idea. And each of these representations are all representations of the same shape, of the same idea. And in VSP, the true geometry is the parameters, the aspect ratio, the area, the sweep angle, the taper ratio, the thickness to chord. These parameters are the geometry. And from that, we generate these different shapes. And that's a little bit different than the way CAD would work. Now, representation has a lot to do with the fidelity of analysis you might use. A thin potato chip type analysis representation for a vortex lattice, a surface model for a panel code, an unstructured surface mesh for CFD that then grows to a volume mesh. And this representation very much has to do with the fidelity of the tool, but fidelity is not necessarily correlate directly to the design stage. And this is a mistake that a lot of people have, a confusion that a lot of people have. But the fidelity does not increase monotonically as you go through design. Sometimes you need to use a high fidelity tool early in conceptual design, and sometimes it's entirely appropriate to use a low fidelity tool very late in the detailed design process. And although that may seem counterintuitive and people don't realize it, this is a well-established idea. This chart is from Lee Nicolai's book, and this is from the 2010 edition because it's in color. But if you go back for the 1975 edition, it's the exact same chart, just in black and white. And if you'll notice over in the conceptual design column, he talks about making these changes with parametric parameters like the airfoil type, the aspect ratio, the thickness to chord. And the output is a feasible design, but it's about what decisions you're making. In the preliminary design, the parameters get a little bit more detailed. The requirements get more detailed. You're making more subtle choices, camber, twist distribution. You're looking at the major loads and stresses. You're zooming in a bit. And then finally over to detailed design, where you're going all the way to what it takes to actually produce and make. And you're looking at all of the very detailed stresses and the final stage. And it may be needed, as I said, you might need to use a high fidelity tool in phase one. There may be parts of a design that need CFD in phase one, in the conceptual design. At the same time, when you're doing the local strength requirements, it might be appropriate to use handbook methods and just a sharp pencil and paper in order to do stress calculations, a very low fidelity tool in the detailed design phase. And we need to break this idea that fidelity increases monotonically with the phase of design. We need to be able to choose these independently. VSP is a parametric approach, and I'd like you to think about parameters as evolving through the design process. And in VSP's case, the shape concept, a component is a wing, combined with the settings of the parameters, that is the geometry, that idea and those parameters. And what we have is that in conceptual design, we have these high-level parameters with the general concept. In preliminary, we get some more finesse, things get a bit more detailed. And then in detailed design, every aspect is determined. Things really go further. And you'll find that, VSP is totally appropriate, I believe, through the conceptual and into the preliminary design process. And at some point in the preliminary to detail, it's appropriate to switch to CAD and not use VSP as your primary model. You may still use it for some of your analyses, but it's a point in time when you need to switch over. And again, the design phase you're in is about what decisions are being made, not how they're made. VSP has come a long way over the years. I hope that introduction gets everybody warmed up and ready for this workshop. This is our 8th workshop. I don't know how many of you have been to them in the past and how many of you made, but VSP has been evolving at a rapid pace throughout these workshops and the years before. And we're now up to version 3.21.2. At last year's workshop, we were at 3.18, and you can see this history going back. I will say that the development pace has been very, very fast. We've been making some progress here at Uber. Justin Gravitt and his team at ESAero deserve a lot of credit for carrying the torch in development over these last couple of years through the SBIR they have with the Air Force. And I'd implore you to look at what version of VSP you're running. And if you're not running version 3.21.2, ask yourself why. And if there's not a really good reason, go ahead and update. There's many bugs are fixed in every version, many features are introduced. Obviously, only the newest version gets any support at all. So please update. There's no reason not to. In fact, since last year's workshop, here's a summary of the features that have been introduced. These are just the biggest, heaviest hitters. We'll be talking about a lot of these throughout the workshop, but one of my favorites is the smart input capability, where you can do simple math on the fly in VSP text entry boxes. We have the generic exec capability so that you can have infinite flexibility on cross sections. VSP Aero has received major updates so that it now does fully general unsteady motion, including rotating blades. The GUI support in VSP itself for VSP Aero has been updated to support rotating blades and unsteady motion. We now have the ability to output trimmed watertight CAD files as a BREP representation to either STEP or IGES formats, including negative components and disk and wake type components, also including the structures. So we can output a trimmed rib and spar type combination to CAD. The API has been extended tremendously, including a full documentation of the API where every function call includes an example. We now are building a Debian package so that Linux users can more easily install and use OpenVSP. We also now include a 64-bit Windows package ready to go for anyone to use. There's a Plot3D import. The human geom has now mass properties, is tied into the mass properties analysis so that your passengers will contribute to your CG and your inertias. The mesh geom and human geom are now included in the dgen geom analysis. There's some prop modifications, and then CST support, the class shape transformation cross-section type has been extended so that it's not just for wings anymore. It now also works in stacks, bodies of revolution, and fuselages. So that's just the hit list, the high list of features that have been added since a year ago, the last workshop 3.18. And along with that, there's been countless bug fixes. Tons and tons and tons of bugs have been fixed. And so with that, there's absolutely no reason not to update. Lots of great stuff to have. And I hope everybody is using the latest, greatest version. I've gone a little bit fast through all of this, but that ends our introductory presentation. The way we're going to work the workshop is all of the presentations, even if things finish early, will start at the scheduled time from the agenda. And so we can jump over to some questions. And if anybody doesn't have any, we will we'll reconvene at in about 10 minutes, if there aren't any questions.
Thanks a lot, Rob. It seems like we have a few of them. One might be more appropriate for VSPRO talks tomorrow, but someone was asking if we can provide deflections for control surfaces itself inside the wing. My response to that was we can do those things in the solver, but not inside the geometry. A control surface is a subsurface. Do you care to elaborate on that at all?
Yeah, I mean that's the answer right now. So right now, the way we deal with control surfaces is for the most part, you model them as a subsurface, which we'll be talking about later today, and also when we do the advanced wing talk, I believe. Um, so you model it with a subsurface, and that's just a demarcation on the surface. So you're marking an area where the control surface goes here. There's no physical deflection. And then that can be carried through to the CAD export, to the CFD mesh, CompGeom, lots of different analysis tools then know about where that control surface is. And then VSP Aero is one analysis tool that can use that information. VSP Aero doesn't actually deflect the surface. Instead, it models the deflection of a control surface by instead rotating the boundary condition, rotating the normal vector. So with just locally on that control surface. So without actually moving it and having to worry about whether the geometry stays connected and is well behaved through that rotation, it just rotates the normal vector in order to model the effect of the control surface. And so, as Brandon said, that deflection is right now in the VSP Aero GUI, where you group control surfaces, and you can then blend them and have different gains, and that'll model the physics of the deflection. In terms of other tools, for example, if you were going to some other CFD tool or some other tool that needed control surface deflections, right now, VSP doesn't know about your tool, and so it doesn't have a way to communicate that deflection information to your tool. And so there hasn't been a reason to have the deflection angle in the control surface itself. And I also think that it's important that you would probably want to keep it out of that because of the ability to do those gains and that ganging and that mixing. For example, it's very realistic on something like a flying wing where you would want to have multiple trailing edge effectors and you would want to blend them together into something that the pilot sees as an aileron input and as an elevator input. And that ganging and those gains and blending them together is something that's not a purely geometric thing that probably doesn't belong in the component information. In particular, if you're in a vehicle where you're, say, blending the aileron with the rudder, now those surfaces are even on different geoms. And so it makes sense to group them and keep those gains separately. Um, Now, if what you were really asking was for a more detailed control surface itself that actually deflects and that represents that in sort of in a 3D way, um, there's some real challenges to doing that. We've thought about it in the past, and maybe that's something that we could look at again in the future. But right now, the best way to model surfaces, control surfaces in VSP, is using that subsurface approach.
All right, thanks a lot, Rob. We've got a few more questions in the social Q&A that we can get to here offline, but for the time being, we've got about 5 minutes until the next presentation. I'm going to go ahead and put this in standby, and we will have the next presentation starting promptly at 11:30. All right, it's 11:30, so we're going to go ahead and start with the next presentation. Welcome everybody. We're going to talk about the improvements to the OpenVSP ground school and some of the work that's been done over the last year. So hopefully the audio quality and everything is still working out all right for everyone online. Again, viewers, if you're just joining in, please remember to set your video connection to 1080p using the gear icon in the bottom of your player. And hopefully everyone can hear me. So, the OpenVSP ground school is intended for improvements in training in OpenVSP. So OpenVSP is accessible and intuitive to even novice users in basic operation, but it contains an extraordinary depth and subtlety that can take years to master. And there's a consistent demand for a comprehensive, multi-format, and easily updated tutorial or manual. And the problem is a written document requires more time and effort than is really available from the OpenVSP administrators or the power users. So we determined that an online training program was likely our best option. So we advocated for program development to OpenVSP's leadership and NASA T-Cubed. And in that first chunk of time, we were able to generate a content map and test website pages, create basic videos, and implement some modifications in the early stages. And we worked with the Langley Site Support Network to find a website format that was responsive, clear, and accessible and robust. So over the last year, content generation and the editing process has gone really well. So there's over 67 tutorial pages created with an introduction and a video, and there are over 140 tutorials expected at the present count for Chapter 1 topics alone. And so far, the ground school feedback has been really great, and the community outreach has increased just by moving on to this. So the vision for this program is to have a formalized training program taking users from no prior use through advanced methods and techniques. So the format should be of the form in a chapter subject topic breakdown with an introduction or a lecture on the topic, a demonstration with video, and a procedure. And to reinforce this, we'd like to have exercises after groups of topics or at the end of a subject to reinforce this learning. And a year ago, we had a draft content structure that was laid out about like this, about 5 different chapters of material that included some of the fundamentals, some design intent analyses, interaction with other programs, advanced modeling methods, etc. And in just Chapter 1 alone, we had a breakdown like this. So it was pretty extensive, and it's grown since then. So there are over 140 topics in Chapter 1 alone at present count, and it's likely to grow. Each of these topics has a lecture, a video tutorial, and a procedure, with exercises at the end of relevant material. So in short, this is a massive undertaking, and it takes a lot of work. So I'm really pleased with how far we've gotten over the last year. But because this is such a large task, the intent is to not repeat work that's already been done, or work that belongs at a different resource. So this training program is not intended at all to replace all VSP documentation. It's a how-to manual with explanations of concepts as needed. Much of the wiki content has already been refreshed and reformatted, so there's no need to redo all that from scratch. Justin Gravitt and the folks at ESAero have already updated and improved that wiki. If you haven't been there recently, please go check it out. It's got a lot of great documentation for OpenVSP. Some overlap is of course expected to provide context or detailed guidance of advanced concepts, but existing resources like the VSP YouTube channel, which you're all on and watching right now, so thank you, the Google group, the Hangar, all of those are linked directly from the training. So anytime you want to go somewhere and learn something new or get more information, you can go there straight from the video tutorials. As a bit of a layout to some of the features of this website, you'll land on the home page, and from there you can get to anywhere you need very quickly. You also have a post page that has sticky notifications that keep you up to date on current information on the Ground School website and OpenVSP events. And you'll see that there's an interactive menu showing your current position in the training. So for example, in this page, we have the creating the wing topic under the basic modeling process subject pulled up, and it tells you where you are in the training so that you can easily go back and review things or move to the next topic. We also have links to a contact form to provide feedback or ask questions. And you also have links to all of the example model files. So all of the tutorials that we've built up on this training website are included so that if you want to go and practice one of the concepts, you go straight to that model, open it up, reinforce the learning by doing as instructed on the video, and then you back out and move on to the next one. And a nice feature is that this site is entirely searchable by keyword or topic or category, so you can quickly find what you need. So if you want to learn about how to model a wing, you search for wings and it will pull up anything that's categorized, says the word wing, etc. You can find it all and navigate through and find what you want. Another handy feature is that this website is responsive, so it works with monitors and displays or tablets or smartphones and smart devices. And because it's designed to work this way, it uses active commands rather than the long press issue on mobile devices. So instead of having a menu where you hover and click on things, you actually have to interact with it in order for it to execute a command. And this is not only useful for mobile devices and mobile menus, but it's also very accessible to folks that might have motor control issues or maybe hearing problems if we need to write things down, or the visually impaired. You can only, via the VSP training website is only going to execute a command if you find it and tell it to do so. So it's really accessible, it's really easy to use, and it's very intuitive. So some things that we have coming down the pipe pretty soon in the near term are to fix the subscription service notifications. Some of them work, and some email providers are filtering out emails from the website, and we're trying to get that chased down so that if you like, you can subscribe to the training material and it will go ahead and send you a notification when new content is added. And we'll be wrapping up all of the Chapter 1 material in the fundamentals. Over the next year, we're going to drastically increase production of the content for Chapters 2 through 5, including a heavy focus on analyses and design intent. So expect a lot of things for VSP Aero or structures or getting things ready for CFD, and how to set up your model parametrically and how to link things together. We also want to start writing up nice detailed procedures for those of you that don't want to follow along on a video and you prefer to just have it written out. And we'll put together practice exercises so you guys can exercise those core topics and reinforce that learning. So what we'll do next is I'm just going to close out this presentation. We're going to go to the website itself, and I'm going to demonstrate some of the features for you in real time, show you how the website works, where some of the features are. And after that, we're going to go straight into a basic modeling tutorial. I'm going to walk through some of the tips and tricks and some handy things that you can do in VSP. And then after that, we'll be moving on into the next set of presentations. So let me go ahead and close out of this, and I'm going to bring up the web page. So hopefully everyone can see this reasonably well, and I'm going to go ahead and share this screen on the team so that everyone can see what's going on. And so here we are. I'm going to go ahead and jump to the home page, and we'll start off from scratch. So here's the home page. You land here on the left-hand side, here in the desktop view. You've got all the links. You can go straight to the OpenVSP Twitter account or the Google group. You can search, and of course you can go to the Contact Us page and reach out to us directly. Now the menu will work by dropping down the content, and let's say we want to look at the basic modeling process and go to shaping the fuselage. Why not? And what it will do is it's going to take you to that training page, and it's going to highlight where you are in the menu. So you can see that here on the left. All of these videos are preset to run in 1080p automatically. So you don't have to go in and adjust your quality unless it's not coming through quick enough and you want to back off to something like 720. But natively, they're going to run in the desktop resolution that they were recorded in. So you don't have to change any of that. And if you want to go, you can go to some of these subject or chapter processes. And if you just want to see what's inside, you can go there. And all of these have a summary of all of the various topics inside that chapter, as well as a link to all the other subjects in this chapter. So it's really easy to navigate around and see what you can get into. But something else I wanted to demonstrate is that the website is, in fact, responsive. So if you drag the size of this to something quite small, you can see what it would look like in a mobile view. If you move it around and make it wider, that's what it would look like in a tablet, and here's your desktop view. So this website will respond to the size of the screen that you're looking at in real time, and it will set it up to have the best viewing experience for you so you can set yourself up. Drop the hamburger menu down, and again, it shows you where you are in the training. So, I hope that was really useful. We're really proud of the Ground School website, and we know that it's got a ways to go. We're still working on getting that up and running, but hopefully everybody is able to use that. And what I'm going to do now is get ready to set up for the basic modeling tutorial, but I'm going to pause in case there are any questions. Rob or Justin, if there are some that you see that they need to ask, by all means let me know on the Teams meeting here, and I'll address that while I'm getting this set up.
Brandon, I don't see any immediately on the NASA site that haven't been answered. Justin, I see that you're on the YouTube questions. Are there any questions there you want to bring forward?
I don't think there's anything at the moment.
So there have been a lot of questions, it looks like, in general about units. So let me talk a little bit more about the use of units in VSP. First, let me draw some small boundaries. VSP proper, so sort of the geometry modeling part of VSP, it doesn't care what units your model is in. So when you type in a wingspan of 3, if in your mind that's 3 meters, 3 feet, 3 millimeters, 3 inches, 3 miles, VSP doesn't care. It's whatever you want it to be. And if you therefore have that as, say, 3 millimeters, then your area is going to be in millimeters squared. And when VSP calculates the volume, it'll be in millimeters cubed. So VSP itself doesn't care. Now, some of the analysis tools do care. And so in those places, there are spaces in VSP typically where you can specify the units. So for example, if you're doing the finite element modeling, the structures analysis that Justin Gravitt will talk about on the third day of the workshop in depth, there's a place where you can tell VSP, the structures part, what units you're using. And that's not only for the length units there, but it's also for the mass and the force units. And what that does is, again, VSP for the geometry doesn't care, but when it then writes out a Nastran file or a calculus file for that finite element analysis, VSP then knows what units to output the material properties in and what units to output to tell Nastran that you're working in, say, inch-pound seconds or something like that. And of course, when you're working with inch-pound force seconds, then your mass unit needs to be a slinch. And so it will figure that out for you and tell it. Likewise, if you're in VSP Aero doing the VSP Aero aerodynamic analysis, almost all of VSP Aero is completely non-dimensional and does not care what you think your units are. So the only things that are dimensional in VSP Aero's input are V infinity, the free stream velocity, and rho. And actually, in many analyses, V infinity and rho are ignored by VSP Aero. So it doesn't even matter what they're set to. You can set them both to 1 if you'd like. For the analyses where it does matter, you just have to make them match, again, what you think your model is. So if your model is in meters per second or millimeters, if your model is in meters or millimeters, then you need to set V infinity to meters per second or millimeters per second to match. And you need to set the density rho to whatever matches your model in a consistent set of units. So if it's meters, then you're going to use most likely kilograms for your mass. And so your air density would be in kilograms per cubic meter. The default value of 0.002377 is the familiar value of slugs per cubic foot, and I know that anyone who works in metric isn't going to appreciate that, but that's the normal value for working customer units for air density at sea level. Again, most of the analyses don't actually use that value, so it doesn't matter what it's set to, but all you have to do is put in your preferred value of rho, and you'll be good to go. I'm trying to think of some other cases where the units come in. Again, when you export to CAD, when you export STEP and IGES files, in one of those, you tell it what the length units are. But again, that's just communicating to the CAD program that's going to import it when it reads in your model, whether it should interpret the units as in millimeters or meters or feet or furlongs or whatever you'd like it to be. So I hope that clears it up. If there's any more specific questions, I'll try and address those as we go.
All right. Thanks a lot, Rob. Well, I've got the tutorials here pulled up, and I'm going to go ahead and start with some of the core concepts in the basic modeling tutorials. Now, the model that we're about to make isn't going to be highly refined. It's not going to be as good as the one on the ground school website because we don't have the kind of time to nitpick all the fiddly bits of skinning and what have you. But what I am going to show you is how you can pull out some reference dimensions and how you can start to place things together in a way that makes sense for your model. So what we're going to do is take a quick look at what the aircraft would eventually look like here. Now, if we fit this to screen, this just happens to be an example transport aircraft that we pulled from online and publicly available information. So you can do measurements and you can match it. And, it's an okay model. It's not perfect. It's certainly not to the CAD level, but for an OpenVSP model, this one isn't too bad. So what we're going to do is just make a new model and start looking at how you would even begin to model something like this. And usually a great place to start is to find some publicly available information on the layout of your aircraft. Now in this case, I've pulled out a 3-view drawing of the aircraft, and in Adobe Reader, you have a measuring tool where you can click and drag and figure out measurements as long as everything is set to scale. Now the way that you can do that is when you open it up, you go to your tools and a measure tool. You actually have to turn this on, and then you have various types and you'll get this crosshair. So if we were to click at this measurement point and drag this over, and you can hold shift, you can see that we can get something pretty close to what's documented. Now the reason that's already coming out this way is because I've set the scale. So if we right click out here, you can say change scale ratio and precision, and you can see that my scale ratio is currently the measured 3 inches that it'll show you the first time you do this on your page, and you can set it to the dimension that you want. Now this is going to have a certain precision that you have, and you can start to use this 3-view drawing to pull out dimensions in your model. So this is a really great place to begin. Another really nice thing that we can do, if we go back to our VSP model, is we can go to Window and Background, and we can pick an image. So let's say we want to start with a top view. Okay, this isn't too bad. We have a nice outline of the fuselage. We've got our wing, our engines, our tails, everything's laid out for us. And if we want, we can add different background views. So before we even add a component, I want to give a quick word on how you can interact with your workspace in a way that makes it very effective. So if you need to, you can scale these and make them bigger or smaller. If you happen to find that perhaps the image itself is not using the correct dimensions in one or the other because either it didn't come into the PDF correctly or a dimension is wrong, you can also give a different scale in width and height. Now, if you go to Window, you can see that you have the option of 1 workspace or 4, 2, and 2. If you break this up into 4 workspaces, and we have all of these here, notice that everything cleared out, but this red box designates your active window. If you click Image, it's now going to put 1 image here. You can click Image, and we can set this one, let's say, to a side view. Okay, we're happy there. Let's do this one. We want to do a front view. So you can see that the scale is a little bit different here because it got a hold of the background and it kind of smashed it because I told it to not preserve the aspect. We can fix that stuff later, but the point is that for each one of these active workspaces, you have control as if it was its own workspace. So in this first, let's go ahead and add a fuselage component, and we're going to jump to a top view and try and line this up. Now, based on our model here, we know that our fuselage length is 124 feet and 9 inches. Okay, that's all well and good. Let's go to our fuselage design. We're going to say 124 feet plus 9 by 12 because you can do smart input math in the parameters now. Press enter and you have it the correct size. And now we can start to line this up as needed. And then we can start playing around with cross sections because now we know one dimension lines up with the view that we want. We can start pushing cross sections around. We can start shaping it by hand if we want. So since I've shown you how to manipulate these in a 4-window scheme, let's go ahead and go back to a single window. And now we can kind of see a little bit more detail of what's going on. So I am going to try and do this with my mouse, but let's say it doesn't like me very well and it's a little clunky. You can always go to View, Adjust, and you can take your zoom, collapse this down a little bit, and you can get some nice fine zoom control over this part and line it up just where you want to. Okay? So at this point, let's go ahead and get rid of Adjust View, go to the cross-section window, and start to play with a few of these. So I'm going to start adjusting the width. And the nice thing is the width is given to me. It's 12 feet 4 inches. So I can just simply say 12.3333 and we're good. Go to the next one or even copy and paste. Okay, we're going to paste again. So now we have a nice width. We can play around with some of the skinning to get things to line up, but we're starting to get there. So next, let's go ahead and change the background to a side view. And we're going to line this up again. We're going to jump to a left-hand view, set things up, maybe give it a little bit of zoom to try and line these things up. And we're just going to continue on. So if we adjust, we're going to move our zoom around a little bit, get things mostly lined up. And the point here is to just show you about what to do, not to really worry about all the little fiddly things. So we're going to go ahead and move this around. And for each of these cross sections, we're going to start to place where they need to go. So let's say that for this one, we want to set our height. Let's give this a bit of positive Z. That's too open. If you click these little collapsible caret icons to either side of your slider, that's going to collapse the range. So you can see now that this is moving much more slowly than when I originally had it. So now I can do that, give it a bit more height. All right, now we're getting closer, and that's about 13 feet. That's not too bad. So let's go ahead and set these to 13 feet as well. Give it some Z. Okay, looking pretty good. All right, so rather than go through all the little details of trying to get the fuselage exactly right, I think by now you get the idea. So we're going to leave the fuselage and we're going to start dealing with how to shape a wing. So in this case, what we're going to do is, as a child of the fuselage geometry, you see we have it selected there. We're going to click on wing and we're going to add. And just because we want to, we're going to say that it's attached to this parent in the component location, and we're going to leave the rotation alone. So let's go ahead and press F5, jump to a top view, and we're going to adjust our background here and bring up that top view again. So now we've got our model lined up and we can start to think about placing our wing. So as a quick word and a little tip in VSP, that if you have a custom view that you really like, say for example a zoom and a rotation that fits your background exactly the way you want to, you can hold Shift and press F1, F2, F3, or F4, and OpenVSP is going to remember that camera orientation, including the zoom and the center of reference for you. So you can press F1, F2, F3, F4 and quickly snap back to that preset view. If you have 2 or 4 of these workspaces open, you can have up to 16 different saved views because, again, each one of those workspaces treats itself as if it's its own workspace. Okay? So that's a handy little trick for when you want to jump around and get a nice clean view. So in this case, we're going to go ahead and start moving this wing back to where we think it needs to go. And if we look at our reference drawing, our wingspan from tip to tip should be about 113.6. So that's as measured. In this case, it's saying it's 112 feet 7 inches from tip to tip. So let's use the reference drawing rather than what the measurement on the paper says. So we're going to set our wingspan under plan. We're going to say it's 112 feet and 7 inches. Okay. So let's do parenthesis, 112 feet plus 7 twelfths, close parenthesis, divided by, I apologize, 112 feet plus 7 twelfths for the total span. In the section span, you would have divided that by 2 because it's only dealing with this right-hand side. But we didn't have to do that, we were doing span. So now we can place this about where it needs to go. And obviously we need a multi-section wing. So let's go here and split. And if we start moving this span back some, now is where we have to start figuring out what the total span needs to be. In this case, let's just eyeball it. That looks good enough. So transform, we're going to move this up. We're going to give this first section a little bit more sweep. And note here we're controlling the sweep about the 0 location. That's the leading edge. We can set this back and control trailing edge sweep if we want to. But for now, let's go ahead and start dragging back. Give this some extra root chord. Perhaps something more like, it's probably about 26, 27 feet, maybe 25. 25 looks good. Let's do that. And then the tip chord, we can just increase until it looks about right. So maybe 12.5. Not too bad. So let's come out to section 2. Again, maybe we have a little bit too much sweep. Let's back that off a little bit and give it some tip chord. All right. So in a relatively short time, we have a wing that looks like it has about the same plan form that it's supposed to have based on the 3-view drawing. So again, note that split gave us that multi-section component. And when we came in, we just gave it a little bit of chord here and there. And maybe it's not exactly accurate because we're eyeballing it, but you can see how easy it would be to go in and adjust these parameters to get something very, very close to what's in your measured drawing. So from here, if we want, we can go ahead and further modify this wing. Let's say we want a front view. And again, let's come to our image and go to a front view. And then we can start placing things where we can start to adjust maybe the thickness, give it some dihedral, and do that. So here, let's go to the Transform tab. We're going to lower this wing just a little bit to maybe there. Looks pretty good. And if we come out to section 2, we can start to give this some dihedral. Now, you'll notice that even though I left everything the same, because I jumped to a different view, my zoom changed. So again, kind of like earlier, I need to tweak this zoom so that everything lines up a little bit better. But for the most part, you get the idea that you can set these up, line things up, and then kind of by hand manipulate these models until they get you what you need. So based on the front profile, it looks like our thickness to chord is okay down near the root and at the tip. And if we want to modify things even further, we can come to the airfoil tab, and you'll notice that each of these has a NACA 4 series. In this case, we're using a NACA 10 pretty much everywhere. We don't have to do that. You can use any one of these different cross-section types to define this airfoil, or you can set things to an airfoil file. Now, VSP is packaged with airfoil files. You can just come here to airfoils, and here's a nice list of already included airfoils. So let's say we want 737A airfoil. Click OK. And if you click Show, you can see what that airfoil likes in the cross-section view window. So you'll notice here that this root section got pretty beefy. And really what we need to do would be to drop this down a little bit more, set that other cross-section airfoil to be correct here, and then modify things accordingly as we move out. But that is how you can come in and modify airfoils in a wing and adjust things. If you happen to know, for example, what your root incidence happens to be, you can give this some root incidence. And if we zoom in, and perhaps let's just get rid of the background, because at this point I think you can see how to manipulate these models, how to match things to a background view and use reference dimensions. Let's just see what changing some of these other parameters does for you. And with some time remaining closer to maybe quarter past the hour as we transition to our next, we can go ahead and answer some of these basic modeling questions that you have. But if we go ahead and just jump back to a color, and let's no-show the fuselage. Notice that when I no-showed the parent, it no-showed everything underneath it. So we can click show on the wing, and now we've got it in isolation. If we come back to the plan tab here, you can see that we can give it some positive incidence, and all it's doing is rotating about the quarter chord of this airfoil, and it's giving it a rotation where the trailing edge is moving downward. So if we happen to know, let's set that to 4 degrees, why not? That sets the root incidence, but for each section, if we come back here to section 1, note that our twist is set to 0 degrees in absolute. If you wanted to change this to relative, let's watch what happens. So I'm going to do another little trick. If you go to the view, you might notice that you can do center, set rotation center, or fit on screen. So I'm going to press R and choose that trailing edge point as my center of rotation. Now I can keep that centered and rotate around and see what I want to see, no matter how closely I'm zoomed in. So while I'm doing this, notice that if I go back to absolute, that airfoil goes back to a 0 incidence relative to the global frame. If I tell it relative, it's at 4 degrees and it's 0 relative to the previous cross-section. So this is an important distinction when you're modeling things like the twist in your wings, is do you want to add some delta twist so that you can prescribe how it moves relative to the root, or do you want to be able to prescribe it relative to your X direction or wherever your orientation your wing happens to be? Because you can combine things like twist, come to transform, and give it some rotation about the Y-axis, and the whole geometry will rotate, but the twist is still the twist. So try and keep that stuff in mind, that when you start combining rotations and transformations and things like that, that whatever orientation it is with the free stream direction or with your global X, Y, and Z may be slightly different because you're starting to combine rotations. So because we went ahead and did that with twist, I want you to also notice that dihedral has the same flag. So back here at the root, we've told it that we want 0 absolute dihedral. Out here in the second one, we gave it about 5 positive. Well, let's change this to relative, and note that it turns relative on for the entire wing. You can't pick and choose. It's either relative or it's absolute. So with relative dihedral on, let's see what happens when I start to give the root some dihedral. Notice that the tip, the angle is changing because it's adding that extra bit. If we set this back to 0, turn absolute on, now if I start to give this extra dihedral, notice that this outboard section keeps its dihedral because it's relative to the absolute frame. Another thing, since we're talking about dihedral, that we really need to pay attention to is you'll see there's this flag that says rotate foil to match dihedral. Now, this is really nice to use, particularly if you're doing something like modifying winglets or trying to put something with a high degree of dihedral and rotation out at the wingtip. So something like a blended wing would benefit from this a lot. But if we turn this on, it's important to note that here at the center, these two, if you're modeling, need to be vertical. So you need to have these things nice and closed. If we were to start to rotate, watch what happens. So because I gave it a lot of dihedral, you can see what's going on here at the root. These two have separated and overlapped. And if you try and run this through VSP Aero or a different solver, it's not going to like this at all. So the way to get around that, if you do want to rotate your foils to match dihedrals, all you do is you just put in a very short span section here with 0 dihedral, and you build off of that. That's going to maintain this center cross section nice and parallel to each other and closed, and you can give yourself relative dihedral as you move outboard. So for now, you notice if we turn that off, all of these different cross sections are all vertical, and that keeps everything tight. So for small dihedral, the small angle approximation means that everything is probably okay. You're not really changing the thickness all that much. But if you give it a whole lot, notice how the thickness is prescribed here. If we turn this on, it makes the wing thicker. And that's because it's using this perpendicular section here. So bear in mind that the decisions that you make in your model, say if you were using this as a V-tail in your model, it does make a difference to the size of the wing and the thickness of the wing. So pay attention to what you're doing when you're putting this stuff together. And while we're on the subject of how to build a tail, let's go ahead and say that we want to show our model and put a vertical tail in this. So the way that you do that, we're just going to add a wing. We're going to come to transform, and we are going to turn off XZ symmetry because we don't need this other side. If we rotate about X in the positive direction using the right hand rule and give that 90 degrees, we now have a nice vertical wing section that we can use as a tail. So in that case, we're just going to take this and drag it way back in X until we're somewhere near the tail. And this is just a piece of the default wing, but we can make it much, much bigger very easily. Let's just give it more span, give it some root and some tip, maybe back off on the sweep a little bit. Okay, so there's your vertical tail. It's as easy as that, but with a vertical tail, remember, don't leave XZ symmetry activated. So if I turn this on or off, you can see it's really hard to see if anything's happening. But what's actually going on, if we back this off a little bit, you can see that there are two coincident surfaces right on top of each other. And that's going to cause all sorts of problems with your solvers or your geometry down the road. With anything that you're trying to make a vertical surface like that, do not reflect about XZ. Now, it's all well and good if you're going to have an offset vertical tail to try and make something like an H-tail. Yeah, go ahead. Leave XZ symmetry on. Make sure that it's about either the global origin, the wing geom itself, or the fuselage geometry. But make sure that your plane of symmetry is correct about the correct reference. So that is how we can go about modeling wing and a fuselage. I know we didn't really go into a lot of the details on how to exactly fit everything. And since we have a little bit of time to go back and look at the fuselage some more, I want to show you some behaviors of skinning. So in the time that we have, I'm going to bring the background back up, and I'm going to go to that side view just so that we can demonstrate a little bit of skinning and how we can do this. So let's jump to a left view, try and set everything up to have an okay zoom level. And you know, it doesn't have to be perfect, but let's just demonstrate what we would do. So I'm going to go ahead and hide these two components and then jump to fuselage, and we'll come here to say cross section 1. Now you can see down here on the bottom that we're kind of matching what we want, but let's come to the general tab, give this maybe a few extra cross sections, and then let this have some more interpolated sections in between this and this point. Now we can kind of see that we're missing out on some of the details here, and we certainly aren't capturing the top of the cabin here. So we can either add a new cross section here and then move everything over, or we can try and just approximate it as best we can. Let's come to skinning and just see what we can see. We know that the top and bottom aren't going to be exactly the same, so we can deactivate top and bottom symmetry, and that gives us control over our angle, slew, and strength parameters. So let's start with the top and go all the way back to the point at our first cross section. We see that it's set to 45, maybe let's bump this up to 90. But that might have been a bit too strong, but the point is that we can just back this off a little bit. So instead of 0.37, let's make this down to, I don't know, about 0.2. Maybe that's not enough. 0.3. Okay, so we're starting to get there. If we come to, let's just go ahead and set this nice and even so we keep our right and left. And now we can start to adjust the strength on our top side. So strength is going to push this out further and further. And there's a nice talk on skinning that explains exactly how all this stuff works in detail, but this is just a quick demonstration on what some of them do. So you can give this just a little bit extra down here on the bottom. We can give this a little bit more as well, and you can see that we're starting to capture some of this shape. If we really wanted to do it right, what we would do is add a cross section here because there's obviously an inflection point, and then you can set angles and modify as this goes around. So back here at the tail, let's go to this cross section. We're going to adjust its position in X by dragging this back a little ways to say here. And we're going to go to this cross section and we're going to raise it up in Z. So once we have this all set up, we're going to give this maybe some more points, back to skinning. And here, let's start playing around with the angle a little bit. So again, turn top and bottom off, and what we're going to do is adjust the angle. So in this case, you can see that changing the angle is going to change how that feature line passes through that control point in the model. And the trick is here that if we know we want it to be 0 on the left, but slightly different on the right, we can turn off this equal sign, and now we can have this be only controlled on one side. So if you happen to know that it's a discontinuity in the angle here, you can set those to be unequal and let it ride. So again, you can adjust your strength, piece everything together as needed. But you can see how if you were to add a cross section here, control your skinning on the top and bottom, and you'll do the same thing for the left and right. It's just a trick of trying to get the closest approximation to this surface using as few control stations as possible. Because you don't need to go in and put 25 different cross sections in here. You just need to have maybe 3 or 4 stations where the geometry starts to change and use skinning to accomplish the rest. And you're going to get a much smoother surface and a really representative surface if you approach it that way. So hopefully that explains a bit of basic modeling and how to manipulate wing geometries and fuselage geometries, how to adjust your skinning, and some things to watch out for when you're doing things like vertical tails, adjusting dihedral, etc. The basic modeling tutorial in the ground school goes into a lot greater detail and walks you through how to build up that 737 model. So if you want to see a lot more detail on how that's done, by all means go visit the ground school and watch the step-by-step. With that, we've got about 15 minutes or so until we start the next presentation. So I'm happy to answer any more of the basic modeling questions that you might have or give some demonstrations of a concept if you like while we start getting set up for the next presentation.
Thanks, Brandon. We've had some good random questions on both the NASA and the YouTube chat lists that weren't necessarily related to basic modeling, but I think we've got those answered. I'd like to welcome anybody out there who has any questions about basic modeling to type those into either one of the formats now, and we'll forward those to Brandon so he can address them.
And while I'm at it, I'll go ahead and look at the social Q&A and see if there's anything that I can answer directly while we're looking at this. Let's see here.
Someone just asked how to get the correct tail angle without adding extra cross sections.
Okay, so I assume that means the correct tail of the fuselage, for example?
I would think so. I think if you might go a long way by just making this this model match the tail angle. There you go.
Yeah, so let's go ahead and take a look at the fuselage that we've already built up. And this example file is on the ground school. This is the exact same thing that you will download if you were to go to the ground school and get the tutorial files. While I'm at it here, I am going to see if I can adjust the zoom and get this to be just about right on. And we'll see if maybe we can't get this just right. Okay, so on this fuselage, you can see that we've got our skinning and our cross-section tabs. Let's go ahead and go all the way to the tail. Now you can see in this cross-section in particular, it's already got a vertical flat section on the top, but it starts to cup up just a little bit here. So in that case, in the cross-section tab, you're going to give it a little bit of Z offset to line up your dimensions with that outer mold line. And then back here, we have another cross-section that's basically the closure of the fuselage. So you can see that the height on this is actually quite a bit smaller than the one prior. And to make this a nice watertight component, we've closed it with a point. Now here, this is all rounded off, but if we go to skinning, we've got the bottom side set to -20, and that's just to try and loft this line down in a nice gentle curve to match what's going on here. If we come back to cross-section 4, you can see that we've got this set to a -5 degree angle. And really, it's just a game of picking the angle that seems to follow this curve the way that you want to go. And then you can adjust the strength. So for example, if I didn't quite like that this had some extra space back here, I could give this a little bit more strength, and you can see that I can kind of push it out just a touch more by adjusting strength rather than dealing with any of the angles. So you can kind of slide this around and move these until you get a really, really nice match on your control surfaces. And while I'm talking about it, let's go ahead and take a look at this, because this is usually a decent indicator on how your model is behaving and whether or not you need to either give a different angle or adjust some of the strength. Notice as I adjust the strength on the bottom side here that these interpolated curves and these stations as I move along either bunch up or they clump together and push out. Okay, so I just did that on the right side, and let's say I did that by accident, which I did. You can either go to Edit and Undo Parameter Change, or simply press Control Z, and it will reset the last change that you did. And that's a handy little feature to have. While I'm on it again, OpenVSP does not autosave. So it's important to save your model while you're working. We've got a nice presentation about using Git to do version control and save your backups later. But for the time being, just realize that as we're adjusting the strength of these, you notice that you get closer and closer. You can actually set this to 0. And that's taking all of these sections as you move back and it's slamming them up against this cross section. And that's going to cause you problems down the road. If you need something to have a zero strength skinning loft, it's a lot better to just deactivate it entirely. So if you just turn off set, it's going to do a direct linear loft in between these components, and you can see that there's no motion, there's no smooth lofting. If we move this around, this is just a straight line from here back to here. So again, if we press R and center this and kind of move it around, it's still not bad, but there's no elegant smooth skinning going on. It's just drawing straight lines and it's smashing everything together. So don't use zero strength skinning is usually the mantra that we go with. Do we have anything else coming up? We got about 10 more minutes before the next presentation.
Yeah, Brendan, we've had a couple of questions. One that would be great for you to address. Someone asked, assuming that you're designing a V-tail, is the sweep angle measured from the XZ projected profile, or is the sweep angle measured from the plane of the V-tail itself?
So the sweep angle in any of your wing components is just going to be that line along the leading edge relative to the geometry. So, like if we rotate it in dihedral or rotate it in Y, it would be like if you're looking at a normal view to the wing. And Rob, if I'm misspeaking here, by all means, correct me. But at least in my experience, I think that's the way it behaves. Is it treats the sweep as if it's the component. Now,
Yeah, I
actually,
think the answer in the way the question was asked is the second one. It's measured in the plane of the tail itself.
right.
The wing is swept back and then it's rotated to put in either the dihedral or if you rotate about the x-axis.
Yeah.
And
So
we've got to thank you on that. So I think it's been understood.
good.
We had another question that was pretty in depth, and I'm going to try and address it. It's been asked on the NASA side. I'll try and summarize it because it's a very long question, and I think it's probably asked by Cal Weller. So the question is about some of the details of the skinning algorithm, and how does OpenVSP differentiate between top, bottom, left, and right curves? And is it interpolated in the U value around the circle from 0 to 0.25 like that? And I'll say that basically, yes, it is. The top, bottom, left, right is specifying the quantity of interest at the 0, 0.25, 0.75, or 0.5, 0.75 and values. So at those quarter values of U, it's mentioned what happens if you rotate that cross section, that section. What happens to the if you spin it versus rotate it? I think what happens to the to the skinning, and I think that spinning and versus rotating about X will have different results. Spinning, it should just take that shape and reparameterize it, so it just shifts where the 0 point is in that U parameterization, and and so what you may want to do is rotate and then shift back. So I'm assuming you're doing something like an engine inlet where you want to have a trapezoidal tilted inlet that then flows into a circle shape. And so in that kind of a situation, you may need to rotate the inlet in X and then possibly spin the parameter back to where you wanted. In particular, in cases where the U value is very nonlinear, it's squeezed in one part. I do think that skinning is going to be a challenge. It's going to be difficult to work with. So there may be ways to try and work around that. And I can probably, if you email me, I can probably help you work through those. The way VSP does the skinning is we lay out that curve. So you can think of at a cross section, there's a curve in 3D space that exists. And then what we do is we also build a curve for the first derivative of the surface at that location. And then we also build a curve for the second derivative of the surface at that location. And there's, of course, in front of the section and behind the section. So we'll actually have to build a first derivative curve in front of and behind the section if those are different. And of course, the first derivative in 3D space means that it's a vector. So it's a curve of the x component of the derivative, the y component of the derivative, and the z component of the derivative. And when we're skinning, we only care about the derivative down nose to tail. So that would be the v or the u or the v, whichever one is not around the circle. So what we do is we have XYZ curves of the position, and then we have XYZ derivative curves, and then we have curvature curves. And those curves at each end of a section are used to specify the shape. And that's what we then do the math to loft the surface between them. So in particular, when we lay out a curve and we know at that top, bottom, left, right point, which are at the 0, 0.25, 0.5, and 0.75 points, we know the three-dimensional, what we want that vector to be, right? By specifying angle and slew and strength, what you're really doing is you're specifying that three-dimensional vector. And so you've got a vector here on the top, and you've got a vector on the side, one on the bottom, one on the right. And those are actually then in a curve that goes around. So those are then spread out. And then what we'll do is we smooth that. I think we actually do it simply linearly. I'd have to go double check the code. But for all those points in between, from 0 to 0.25 to 0.5, we're going to linearly vary. So if the vector points in this direction in 3D space at 0, as you move to 0.25 and it points in this space, we're going to linearly vary that vector and create a bunch of vectors all along. And so we have this we end up with a continuous specification of the derivative all the way around, and that's what's used to loft. And I know that that's a deep in the weeds answer, but hopefully that's helpful.
And I also just realized that my microphone was muted. So to those of you online that just missed what I just said, we will be going on standby for just a couple of minutes so our talk can begin at 12:30. We'll be with you in just a moment. All right, everybody, welcome back. We are at 12:30, and we're going to go ahead and start the attachment presentation with Rob McDonald. So with that, Rob, by all means, take it away.
Thank you very much, Brandon. As Brandon said, I'm Rob McDonald. This presentation has a lot to it, and we'll start with a bunch of slides that I hope will make everything clear. And if we have enough time, we'll try and do a quick live demo that will demonstrate a bunch of these features. And this is sort of a grab bag of features that allow you to better set up your models to capture the designer's intent, and that allow you to organize your models in better ways. And so we'll be talking about attachment, hinges, symmetry, sets, and subsurfaces. So without further ado, each component in OpenVSP is placed in the world based on its attachment point. And so what you'll see when you add a component, there's the global orientation shown down in the corner. And anytime we show one of these orientation triads, we use the colors red, green, blue to represent X, Y, Z in that order. So even though it's not labeled, this dash triad, you see red, green, blue, you know that's the X, Y, Z location. In this case, this pod is positioned relative to its attachment point. And when you position a point with a relative button, that's what it's saying. We are 2 units in the X and 2 units in the Z relative to its attachment point. Normally, of course, the default is 0, 0. So when a component gets added, its attachment point is drawn right at its nose. And then what you can do is move a point relative to its attachment point. And then, of course, attachment allows you to move where the attachment point is. When you place components in the tree, in the Geom browser tree, what you'll see is you can place them in a hierarchy. So you can make a component a child of another component. And when you do that, you then have the option of attaching it to a parent. You don't have to. You can just use the tree for organization, but you can also use the tree for attachment. And so you can only attach to a parent. And when you do that, you'll notice that there's a little caret that gets displayed. So the second pod is attached to this parent pod. And in this case, what we have is the green pod, which is the one that's selected, is attached to the gray pod. And so we notice the green pod's attachment point is located right here. And we've done this because you'll notice in the attached to parent section down here of the transform tab, it has been attached in both translations and rotations to the parent's component coordinate system. Your choices here are none, don't attach it to the component coordinate system, or attach it to UW. We'll talk a little bit more about what that means in a moment. But so we've attached, and then you can separately choose to attach translations and rotations. In this case, both are attached to the component system, and then it's moved relative to that to 2 relative to that. So that's why it's not located at its dashed triad. You'll notice its absolute coordinates then are actually at 4, 4, and that's because this gray pod was located 2, 2 away from the origin. So 2, 2 away from the origin, 2, 2 to from the attachment point locates this green pod at 4, 4. When you attach any UV coordinates, what you're actually doing is you're placing the attachment triad somewhere on the surface of the parent. So instead of it being measured relative to the parent origin, which is at typically the nose of each component, the UV coordinates run from 0 to 1 along the surface. So U and V, one of them runs from U, in this case, runs from nose to tail. And so you can see we're basically 5% along the length. And W runs circumferentially all the way around from 0 to 1. So here we are 90% of the way around, and it looks like it's going counterclockwise. So at 90% of the way around, we're almost back to the beginning. So we're almost back to the top. I think that's the right orientation. And since we've both translated and rotated, you'll notice that this UV coordinate system is tangential to the surface, with the X direction running in U, the green, the Y direction running in W, and blue, the Z direction running normal to the surface. So what we have is we're slightly offset from the nose in this coordinate system, and then the green is 2, 2 in XZ off of that. And that's why you notice that the absolute coordinate ends up with these odd values, and it's because of this rotation from this point. But you can use attachment to attach to the surface or just the origin of an apparent component. Now, there's relative and absolute as a choice in what you do. And this can be a little bit tricky because when you're not on this tab, if you move a parent component, no matter whether it's relative or absolute, if you've used attachment, it's going to move. The attached component always moves when the parent moves. But what this does is it allows you to type in the value in a relative sense or an absolute sense. For example, and usually you'll use relative here, but and so you'll set the attachment point like we said, and then you'll set the relative offset. But occasionally you may know that you want to attach something either in component or UW way, but then you also know from, say, another 3D model, a set of drawings, or something else, you know what you want the absolute orientation and position to be. So what you can do is you can set that attachment, change it to absolute mode, type in the exact values of the XYZ and the rotations that you want, and we will actually back solve for the relative required to do that. And so what this actually does, it should be pretty simple, and it is when you get used to it, but it actually allows you to do some very powerful things by changing between absolute and relative as you move along in a model. So there becomes sort of a hysteresis here, and you can change the structure of a model, change the parent-child relationships, move components around by switching them, say, to absolute, turning off the parent-child, moving what it's a parent or a child to around in a model, reattaching it, and then setting it back to relative again. And that'll become more clear when you play with it or when I do the demo. There's a special kind of component in OpenVSP called a blank, and there's no actual geometry to a blank, but what a blank is really useful for is inserting its own coordinate system. So if you want a part or a component coordinate system, you can name that blank, use it to group components, and attach things to them, and it will build up and show you that for that blank. And you can also use it for a point mass and mass properties. And when you draw a blank, when a blank is visualized, the attachment point again is shown with the dashed triad, but then the blank itself is shown as a little red dot with a solid line triad so that you know where the blank component is and what its orientation is. Somewhat more complex, but in a similar vein, there's also a hinge component, which can also be used as a one-dimensional linear slider. And if you want to build any sort of articulation into your model, whether it's a tilt wing, moving landing gear, folding wing, anything like that, you'll want to use a hinge to do that, or a slider. And so you can add simple motion, and a hinge is kind of like a blank in that there's no geometry. It's just used for coordinate system building up. But there's a few things that are different. First, notice that a hinge, there's a double arrow. And what that means is the hinge forces all children to always be attached to the parent. It just doesn't make sense to have a hinge where the children are not attached. So that gets forced, and the double arrow represents that forcing. When you're thinking about a hinge, you need to think about a fixed side of the hinge and a motion side of a hinge. And I like to think about this in terms of the hinge on your door of your house. The door of your house, one side of the hinge is screwed into your house, the door frame, and that is the fixed side. And of course, the other side of the hinge, the one attached to the door, is the side that actually moves. So that's the motion side of the hinge. And in the hinge component, what you have to do first is you specify the fixed side. So it can be attached to its parent and move relative to that and get its orientation. And then you specify the position and orientation of the hinge. So that's the rotation axis and where it starts. And that's specifying the fixed side. And then the motion side is then either rotated or, if there's a slider, translated relative to that. And you'll notice in this, the attachment point is this long dashed line. The hinge fixed side is a solid line. And then the short dashed line is actually the motion side of the hinge in its moved point. When you're setting up motion control, we default to a hinge, and there's you can control the rotation, the translation of similar controls. There's the ability to set the minimum and the maximum angle for the rotation to go to. That way you can build that knowledge in your model into the VSP model. And you can then change the rotation between those stops very easily. There's also the rotate slider, which actually controls the current angle. You can turn on or off these limits by hitting these buttons, so that you can, if you don't want there to be a minimum angle, you can turn it off. There's also this set button, which if you dial in the rotation, let's say you dial this into 22.86 degrees, and you decide that looks really good and you want that to be your minimum angle, whatever it's set to, if you then click the set button next to min, it'll assign that value to the minimum. And likewise, if you then move it up to 64.3, you decide that's the maximum angle, click the set button and it will set the maximum to match that. So you can set those. And then this range button, what that does is it sets the range of the slider to match the min and the max, so that when you move the slider all the way to the left, it corresponds to the minimum value. And when you move the slider all the way to the right, it corresponds to the maximum value. So using these buttons, you can sort of tailor the operation of these motion sliders. There's a lot of ways to specify the hinge orientation. If you just think about a vector in 3D space, you can specify that vector through a set of Euler angles. You can specify it through XYZ components. You can specify it as starting at one point and ending at another point. You can specify it based on a normal vector to a surface, etc., etc., etc. And so VSP, the hinge, allows you all of that control, and it gets a bit confusing, but this input allows you to basically, if you want to use just angles from the XForm tab, you click rotations here at the top, and it uses the XForm tab just as any other component. Otherwise, if you want to use this tab, which is a little more complex, you choose the vectors button, and it uses this GUI to specify the angle. This vectors section tells you which axis you want to rotate about. Do you want to rotate about the X, the Y, or the Z? And the reference tells which direction the minimum and maximum angle are measured relative to. So the 0 direction, in this case, we're going to be rotating about the X in the triad with our angles measured from the Y. And so that's always, and these are grayed out because you can only choose different choices. So this axis and reference will always be shown, but down here will be the different options for how to specify the vector. So you can either do a 3D vector, you can choose a point in 3D, you can choose a point on another surface, or you can choose the U, W, or normal direction from another surface. And all these options allow you to choose what is that other surface that it's normal to, an offset from it, an XYZ point, start and end, the UV, etc., how to do that. Here's an example of a hinge, and I'll do this live when we have a little bit of time for the demo in a moment. But I've got this example where first we have a simple hinge at the tip, where you can see the rotation is sort of aligned with this chord. And so the tip folds in, and it's set up to fold all the way over, and its position is actually aligned with the top surface of the core of the airfoil. So you'll notice it's a little bit offset here. So it folds over until the wing folds flat on top. And then this also has a Grumman fold. So this hinge axis is 45 degrees in and down at about the quarter chord in the center. And that causes this wing leading edge to fold down under until it's back parallel to the fuselage. And so this is a wing with two folds. First the tips fold, then the rest of the wing does a Grumman fold back along the body. I'll show you this demo in a minute. Symmetry is another great way to build design intent into a model, and components have many options for single symmetry. So we don't really support multi-symmetry, or at least symmetry about multiple origins, but you can have multiple kinds of symmetry about a single origin. And so each component that you want to be symmetrical, you need to think about, is it going to be symmetrical about its own origin, its parent's origin, its grandparent, how far back of an ancestor, or all the way back to the global ancestor's origin. And then it can be either planar symmetry or axial symmetry, where you specify the XYZ axis and then how many rotations to make it like a flower petal. The origin is chosen so that you choose itself, in this case a power face. It can be about itself, which is going to be 1. Me, myself, I'm 1. My parent is 2. My grandparent is 3. My great-grandparent is 4. So you go up the hierarchy that way. The global origin is always a choice, and it's always 0. So you can choose that as what you have your ancestor symmetry about. And then, of course, each of these levels, for example, the pylon, it has its attachment point and also the object itself, its own coordinate system. And so you can choose, do you want to be symmetric about each component's attachment point or its own origin? And you can use that to build up any level of symmetry you want. Changing gears a little bit, sets are a really important thing to learn as you're using VSP to do engineering analysis. So you're not just building a pretty 3D model, but you're doing something with that model, some sort of analysis. So sets are a way of organizing a model by purpose. So instead of it being a hierarchy by geometry, we're now going to organize components by what you're going to do with them. And one of the ideas of this is not all the components are needed all the time. The outer mold line, the OML, is needed for aerodynamics, but if you have a passenger inside or radio or an engine represented internal to the airplane, then you don't need to represent that in the OML set. And so since you're doing different purposes, when you're doing aerodynamics, you need one set of components. But if you're doing mass properties, then you may need the equipment and the payload and those things that are internal. Different sets for different purposes. Any geom can be a member of more than one set. Sets get names, so you can name it by that purpose. You can call one the aerodynamics set and another one the mass properties set. And then actions, think of this as a verb. You do things to sets. You take an action on that set. Sets show up all over in VSP. They're pervasive, and you can use them all over the place. Any analysis you do in VSP, you're going to have a little pull down to tell it which set you want to do that analysis on. Every export option, there's going to be a set. And if you're using the API, you're going to specify which set you want to act on all over the place. Another trick thing to do with sets is you can have what I call pseudo-duplicate components. You can have two versions, Dr. Jekyll and a Mr. Hyde, of certain components, and then they can be in different sets. So for example, you might have your real wing in one set, but you might carry a simplified reference wing in a different set. And that includes different, a simplification of that plan form and other things like that. In general, sets are a power feature. This is an advanced thing, but if you're using your models to do calculations, you're going to find that you absolutely love sets. Once you understand them and use them, you won't ever go back. You won't know how you ever worked without them. They're really key to being a power user with VSP for analysis. I'll give a little bit more detail on sets. You can pick which sets a geom is in right from the geom editing window. So for example, in the general tab, there's the set list down at the bottom, the set chooser, and you just click which arrows you want any particular component to be in which sets. So in this case, we have AVL, Parasite, Airspace, and Battery as sets that we've named. And this front wing is in 3 out of the 4 of those. And so geoms can be members of more than one set. The geom browser itself, which has some of these really commonly used functions like show, cut, copy, paste, and controlling the visualization like hidden shade and texture, sets are important enough to have made it right here. Down at the bottom, there's an area for working with sets. You choose which one and it'll show that list, AVL, Parasite, Battery, etc. And then you have these fundamental actions that can be done on sets. You can show only a set, you can show a set, no show, or select all of a particular set. In fact, under the hood, you don't need to know this, but show and no show are actually implemented as sets. There's special sets that we're constantly putting components into and out of to control that visualization. There's also the set editor, which you access from the model window. And so you click Model Set Editor, and it pulls up this window here on the right. And you can use this to change the name of a set. This is the only place to name a set. So you come in here and you name them. You can manipulate the membership by choosing then, if you say come to the Parasite drag, and you can turn on which ones you want in Parasite drag. There's some other manipulations. For example, you can add everything to a set, remove all. You can copy the members of one set and then paste it into another set. You can select a set from here. And then you can also choose when you copy a geom, do you want to copy that set membership? And that's a behavior that we thought users may want it one way sometimes and the other way other times. So we make that an optional control here to control that behavior right from this GUI. Changing gears again, and really one slide is not enough to do justice for subsurfaces. But subsurfaces will also come up in some of the modeling. But what they allow you to do is demarc an area on the surface of another geom. So here's a pod, and here in UV coordinates, we've drawn a rectangle and an ellipse on that pod. And this subsurface, we've marked an area on a surface, and that can be used by different analysis tools for, say, for mass properties. You might, not our mass properties, but you can imagine different boundary conditions in an arrow tool. You could say have an actively cooled patch on a high-speed vehicle, so that you have part of it is actively cooled and other parts of it are passively cooled. So you're applying different boundary conditions to CFD. This is how we mark out control surfaces for deflections in VSP Aero. And you can also use them just as something visual. You can use them to draw windows and doors on your airplane by using subsurfaces for that. The subsurfaces are carried through to some of the modeling, some of the different analyses that we do. When you do comp geom, for example, it'll obey and it will split the triangles to mark what's in and out of each subsurface, so that you have tags that tell you where the pod itself is, where the rectangle is, where the ellipse is, and then notice even separately where the union of the ellipse and the rectangle are. In a similar manner, CFD mesh obeys those kinds of rules and will mark out and make a mesh that obeys subsurfaces. You can use them for all kinds of purposes, and they come in very, very handy. And with that, I'm going to fire up. I've only got just about 5 minutes for a quick demo. So I will try and just show a couple of quick models first. And if there's any questions, Brandon, you can ask them to me verbally while I open this up.
Yeah, we had a quick question that said, are child components automatically added to the set that a parent belongs to?
They're not. Right now, when you add a component, there's it's not a member of any set except for shown. So here's that compound fold model that I talked about earlier. First, we'll look at the fold out here at the tip. You'll notice that it shows the rotation axis. So we're rotating about this red axis, the X, and the X-axis goes right down the top of this wing surface. If we look at this fold hinge right here, and we look at its orientation, we're just using the X-form tab to locate it. And here we've actually translated it on UV. So we've placed it at U of 1. So that's all the way at the tip of this inboard wing section, and W of 0.5. That means all the way at the leading edge. So we've attached it right there. And notice we've attached it differently. We've attached it in UW in translations, but the component in rotation. So that's why it's still straight and aligned that way. Then we've bumped it up in the Z. We've incremented it in the Z half the thickness of this airfoil, so that we came up that 0.125 to get it lined up right there. And so we've got that perfectly aligned the way we want it. And if we come out here to motion, you'll see its limits are set to 0 and 180. And if we click that range, and as we fold it, we're rotating about that point, you'll notice the dashed lines, which are the moving side of the hinge, and it folds right over until it lays down on top. We want 180. Looks like we could actually go a few more degrees if we wanted to compactly tighten it, back it down. Now that we've folded that, we can take a look at our Grumman hinge. That's a little bit more obscured by the geometry, but notice we're again rotating about the red axis, which is oriented pointing, if we sight along it, 45 degrees in and down, which is the way a Grumman hinge works. We set this up. Its attachment point it's attached again in UW to the parent, to this inboard section relative to the leading edge. So notice its attachment point is right here. And then what we've done is we've translated an X, so we've moved it 0.75, which is down to the quarter chord. And then we've rotated 45 minus 45 to do that in and down rotation, so that we actually use the X-form type rotation for both of these. We didn't use any of the more advanced. And so then when we want to move this, we've already set our limits, our min and our max, to minus 141. If we click that range, but so now as we rotate back, we're rotating about that axis. This isn't the best view. Let me say look from the front and down a little bit, say about there. As we rotate it, that tip droops down, folds back parallel, and in this case, we've folded it back along, and we've got a lot of sweep. That's why it looks a little bit different than you might be familiar, but we folded it back parallel to the body and along the aircraft. So that's using hinges and attachments in this model. While we're here, let me open a different model that shows some use of sets. This is I'm opening one of the models that Uber has released of some of the concept vehicles from a couple of years ago. This is the ECR M3. Let me shade all of it, and I just chose it because it's a model that had sets used from the start. So here you can see we have AVL, parasite, airspace, and battery. So if we want to look at the AVL, we can show only those components, and these are then the components that you would then send in a model to AVL. Whereas for the parasite drag, these are the components that are in the parasite drag model. And the airspace model adds the propeller, the propulsion components, and the battery model just has the batteries only. So we've used these sets to group, again, to group by purpose, by function, what we're going to use these for, and then we use that to feed to different models. And with that, I'll wrap up this particular talk.
All right. Well, thanks a lot, Rob. That's quite a lot of information, and we probably could have given a good bit more time to a lot of these talks, but because there's quite a lot of content in the workshop this year, we can always answer these things on the Google group, or of course in the Q&A forums that we have going right now. So we are right at 1 o'clock. Let me go ahead and just bring this screen up for a moment. So if you haven't seen it yet, if you go to the OpenVSP Workshop main page and the VSP DocuWiki Workshop 2020, it's got all the links to the various sessions and the schedule. So you can see here we're at 1 o'clock. I'm about to talk about Git version control of VSP models. So by all means, jump to that webpage if you want to see where we are in the workshop and what's coming up next, or if you want to schedule when you need to come back to see a particular talk that you're interested in. Let me go ahead and come out of full screen mode, and I'm going to move my presentation up, and we'll go ahead and just roll into the next talk. So here, let me also share my screen so that everything should be up and running. Rob, can you see my screen? Is everything good to go?
Yep.
All right, wonderful. So what I'm going to do now is talk about using Git for OpenVSP model version control. And Git is a version control and file control system that allows you to branch apart and make changes to your models without actually affecting the source itself. So for a bit of a discussion here, we're going to go over why we would use Git, a little bit of the nomenclature associated with Git processes, and some different flavors that we have of Git and how you can use those. And at the end, with time permitting, we're going to go ahead and do a demonstration using GitHub Desktop and show how you can make some changes and do some version modeling in real time. So in this case, we're talking about version control for models rather than for software source code. So this can include things like your VSP geometry, various performance models for different software, your design inputs, notes, scripts, etc. All of that can be version controlled in the same directory. And this can apply to a single designer or multiple designers working on a model. So each individual can modify the model as they need at the same time and then merge those changes together when it's complete. So this enables extensive collaboration of very complex OpenVSP models or libraries. And this avoids the tendency to save multiple copies of the same model as the design progresses, to where you go, oh, well, I want a backup of this. So I save the new one after I've made some changes as some elaborate file name, and eventually you have no idea how you got there or where you made a change. This alleviates all of that, so you don't have multiple copies of the same thing cluttering up your workspace. So why use Git in particular? It's because it's a simple, clean, and easy to use version control of a variety of file types. And you can save the files as much as you want without affecting the stored version in your file structure. So if you make a change to a VSP model, for example, and you save that, you can always reset all of those changes back to before you did what's called a commit. So you can modify as much as you like without fear of losing your work at any point in the model chain. This is also a highly collaborative environment for user-controlled resources. And you can work locally on your laptop or online at, say, GitHub or GitLab, and the changes that you're making are tracked on both. And when you're checking out a copy of a repository online, you're not only working with the piece that you're dealing with, you're working with the entire history of the project. You can see every change that was ever made, and this is called Distributed Version Control System, or DVCS. So there are multiple backups of the project in case something is corrupted or lost, say on your machine or on a server. There's always something somewhere that has the entire project history. And of course, the OpenVSP source code is on GitHub, and it's at that link right there. So the nice thing is that VSP models are essentially an XML-based code. It's all human-readable format. And in fact, few VSP files are unformatted in a way where you couldn't just go in and read what it is if you understand the syntax and the language. Now, you can version control everything in the repository, including things like VSP scripts, Python code or scripts, MATLAB codes, design files, variable files, configuration setups, analysis input and output files. And you can also put things in there that are unformatted or binary files like PDFs, images, Excel, etc. The thing is that the unformatted or binary files are tracked, but you don't necessarily see the differences because it's not human readable. It can't do a diff operation between those two and tell you exactly what changes. It just knows that it did. But there's nothing at all wrong with keeping those files inside the repository so that everything's in the right place. And the documentation uses the markdown language, which is very useful for keeping a summary or a description README file, so you can always see what's going on and what the model is about. So, a bit of nomenclature when we're just talking about things with Git. Branches are basically parallel versions of the project where you can safely make changes and experiment and fix bugs, doing things like that, without having any effect on the master copy of the project. So it's just I've checked out a version of this to work on. A fork is a term that implies making an online copy of the main repository. So instead of it belonging to the collective group, you've taken that and you've split it off and made it a completely different copy. It's not checking out, it's a different operation. When you clone something, it's making a copy of the online repository to your local storage. So you're going to clone that online repository and it's going to build everything right there on your machine. And when you check out, that's working with a specific branch, or you can create a new branch when you check out. And one of the really important ones is this term called commit. And a commit is when you say that you want to add all of the changes that you've made up to this point into the project history. You're happy with it, it's stable, it's exactly the way you want, and so you commit those changes to the project. And with a push or a pull, it's either pushing changes from a local copy to an online repository that you have stored, or you can request that people pull the changes that you've made into, say, the master branch. So a few different flavors of Git that are available are, Git bash, and this is a Linux style command structure. It's essentially a terminal that lets you operate in Git and manipulate the repository in a command line structure. And typically this is quite a bit quicker than using a graphical user interface or a GUI. So in this example, you can see over here that we've got the master branch, and we make some changes and we make a commit, and this entire string here is the commit hash ID, or the SHA. So it gives an identification key to each change that you make so that you can track it, see what happened. It says who did it and when it happened, as well as a description and some details. So you can do all of this in Git bash, and there's actually a handy little cheat sheet for Git bash located here. So some useful commands in Git bash are all listed here. This stuff has more to do with initiating a repository or cloning a repository. Most of this stuff down here is how to interact with the repository. So to branch or to check out, to pull or push. And if you do log, that just shows the commit history and it tells you what happened and when. You do git commit with a descriptive message, and that's going to actually execute the commit. And we're going to go through how to use this stuff here in just a second. So an example workflow in Git bash would be to go to your project directory and initiate, say, my project repository. Then you can add stuff in there. And if you do a git status, what it's going to say is, here are some modified files that I haven't committed yet. These haven't been staged, but they have changed. When you add the file names, it will stage these and be ready for a commit. So they turn green and they say, I'm ready to go. I know what I am. I know what changes have made. So you can add them one at a time, or you can add multiple files at once. You can do an add star.vsp3 or a VSP arrow file, or you can just do git add dot, and that adds everything at once. And then git status again shows that these are good to go. Following that, you can do a git commit m and then type your message, which is just what it's called and then a short description. Or if you just type git commit, it's going to bring up a Vim editor where you can type things like the first line is the summary, and then all of the details can be added in the Vim editor in a human readable and easily seen format. So you can provide some detailed description, you can make an enumerated list of what happened and when, visual separators, etc. Now, because this is a Linux style, remember that to save is just a colon write quit or WQ, and all of that stuff works out. So it's really good practice to add details into each of your commits so you really understand what happened, because nothing's worse than going back 6 months later and having no idea what change you made or why something happened. You're completely lost. So be detailed in your comments. The online version control and collaboration happens mostly on GitHub and GitLab. And similar to other systems, there's a multitude of helpful online tutorials present and available. You can find those examples online. And there are step-by-step instructions on navigating and how to do operations in Git Bash and work with GitHub, etc. But a lot of the operations in GitHub and GitLab are point-and-click steps. But what's nice is it's helpful in examining the status of the project. They have visualizations on who has what checked out and where it is, how many different branches there are, what version it is, and it has handy visualization so you can see your current project status. It's a really great tool. So in GitHub, you can add saved files and drop them in. You can perform commits by adding a summary message here and then some extra details. And you can either commit directly or create a new branch and then a pull request. So that has to do with making sure someone else can second check what it is that you've done before it actually gets merged into your master code. So GitHub actually offers an enterprise service to where you can do things like SBU and ITAR codes. That is a paid service. So if you happen to be out in industry and you want to be able to use it for that, GitHub does offer that. And I think GitLab may as well. GitLab is very similar to GitHub. It's got the same type of GUI interface where you can drag and drop, type things in, and do commits. GitHub Desktop is a nice little mix between a GUI and all the controls that are available in Git Bash. So it'll give you a quick navigation of a repository. It gives you automatic visualization of the differences in your various version files, and it's found here at desktopgithub.com. So, for an example, let's say that we're working in a repository and we have an aircraft, and it will tell you that you have a changed file here. And over here on the right side, it will tell you exactly what changed, including, say, you changed the name of a component, you changed some camera angles, various things. So it also tells you what branch you're working in. So all of that stuff is included in this window. You simply type your commit summary and all of your details and click commit to master. And the next thing that comes up is your history. And it tells you what changed. It tells you your 7-digit hash ID, which is actually just a partial of the full commit SHA. And you get your entire history log here on the left. So all of your details are here. And again, you can go back and see exactly what changed. So in this demonstration that I'm about to do, we're going to open up an example repository. We're going to open a VSP model. We're going to manipulate it a little bit and then save it. And we're going to view those changes, and we're going to stage a commit and then look at the view history. So I'm going to walk you through the process for how to use GitHub Desktop and use a model in a repository. So for that, I'm going to go ahead and escape out of this, and I'm going to bring up GitHub Desktop. So in this case, we're working in my Git demo, and I have no changed files. And this repository is here. So I'm going to open my test aircraft VSP file. Okay, so here I can make this view a little bit bigger, and we can see what this looks like. I just quickly press F to center everything in the screen and fit, and we can see this model. So let's say, for example, we want to go into the wing, and maybe this is too low of an aspect ratio. We want to widen this out just a little bit and maybe give it some more sweep. Why not? It doesn't really matter for the demonstration here. So let's give it maybe a little bit more span and maybe a little bit less root chord. And that's not too bad. Sure, why not? And while we're at it, let's give it just a little bit of dihedral. Okay, so we've made a couple of changes, and let's say that we're happy with those. We can go to File and Save. And now, if we come back, notice how it automatically picks up on the file that's changed. It knows that I changed my view center, but if I start coming down this way, it knows that I changed a little bit of paneling. I changed the area, aspect ratio, the chord, some dihedral. There's a bunch of stuff in here, and it's tracking it. Anything in green is what it's set to now. So you can visualize everything that happened in this model. So now we can just say that the summary is to modify the main wing, and the description perhaps is that we added dihedral, we shortened the root, and increased span. Okay? So I could enumerate this. I could make it perhaps a little bit cleaner, a little bit nicer, but for the purpose of the demonstration, you can see what we're doing. All we have to do now is commit to master. If you want to make sure that you're not adjusting the master branch and you want to do something different, you can always make a new branch, then make the changes, which is really the better practice. And then once you're satisfied with all those changes, you merge it back in. So this way you can manipulate things in the model and even make changes to the repository without affecting the master branch. And then when you're happy with the history, you merge it in. But for this demonstration, we're just going to go ahead and commit directly back to the master. You can see that everything is up to date, no local changes. It's offering me to publish onto GitHub if I want. But here in the history, you can see all of the changes back to when I first created this over a year ago. And each one of these has the history. And each one of these I can reset to this stage in the model development. So you can see that it's got my summary here and all of the details included. It's got my hash, it tells me what happened, etc. But I can go back and look at this at any time. And no matter how much I go in and change the model and save and manipulate things, if I'm not happy with those changes, I can simply reset. I can clear all those changes out and come right back to this point. So you can see how useful it is to be able to control your OpenVSP models in this way so that you don't have a bunch of backups of backups of backups. And if you happen to have a model development process to where you need to understand the heritage of how you got where you are, this history can be written out in a human-readable text format where it tells you what happened and when, and it gives you the entire history. So you can write this out as a document and append that onto, say, a presentation or with a report that says, here's my model, and this is every single thing that I ever did to get it to this point. So it makes it traceable. And a lot of control teams, a lot of design environments, that's incredibly important. So Git becomes a very useful and very powerful tool in maintaining traceability and version control of all your models. So we're a little bit past, quarter past the hour. I've given this demonstration here. I know that we kind of rolled in from Rob's talk into this one, so I think I'm going to take some time here to answer a few questions if I can. And then what we might do is break somewhere near about 20 past the hour, and we'll start up again around 1:30. But for the time being, let me go ahead and just answer any questions that might be out there.
Thanks a lot, Brandon. I don't see any questions. Let's see, one just came up here. Oh, just thanks for the GitHub tricks on using the model. If anybody else has questions about using version control with VSP models, now's a great time to ask them, or anything else that you might have about what Brandon said so far today. While we're at it, in general, those of you who didn't join us at the very beginning, to get the highest quality stream, you need to tell YouTube to use the HD option. There's a little gear in the bottom right corner of your YouTube stream, and by default, it might be on low D. And if it's on low D, you're not going to be able to see the screen very sharply when Brandon does a live demo. So be sure to switch it to HD if you haven't done that already.
All right, let's see. No, so far I'm not seeing any extra pop-ups. For everybody out there following along on the YouTube Live, I did post a link to the NASA OpenVSP Workshop Social Q&A if you prefer to use that, where it can have almost like a sticky post that we can upvote and see, because depending on how busy the YouTube live chat happens to be, it might get lost in the queue there. So if you have something that you really like to be answered eventually, go ahead and pop that over, because the NASA social Q&A is the one that we're going to be writing out the report at the end of the day and saving. I'm going to try and make sure that some of the chat from the VSP Live is saved as well. It should be, but I'm not certain. So we're going to be trying to keep track of all these questions and answers so that you guys get this stuff in real time, and we can save it so you guys can go back and reference it later. It says, We've got a question here in the YouTube Live. It says about the hinge component. Can the hinge translation or rotation change during an evaluation, like you can set for range in an angle of attack or mock? So I wonder if they're asking if that can change in between or iterate in something like maybe VSP Arrow, perhaps?
I think that is the question. So I would say that VSP Arrow doesn't know about your hinge and about your model. So although VSP Arrow can easily sweep alpha, beta, and mach, it doesn't have the ability to say sweep an F-14's sweep angle on the wing or V-22's tilt angle on the nacelle. But that said, you can certainly change it yourself manually and run a hover case of a V-22 and then run a cruise case later. And you could also certainly use the scripting that we'll be talking about on day 3, either through VSP script, which is built in Python or MATLAB using the API, to run a VSP Arrow analysis, then change that hinge angle, then run another analysis, then change the hinge angle. So you can certainly do that. Also, later today, one of the talks I'll be doing, the design variables, I'll also be talking about variable presets. Variable presets are useful because when you have an articulated model, because you can set up different configurations of your model. For example, in a model that had both flaps and landing gear, you could have separate configurations for taxi, takeoff, landing, and cruise, where those all have the appropriate settings for gear up, gear down, and flaps in either the stowed, takeoff, or landing positions. So you can, and we'll talk about that during the design variables and presets session later today.
It's about 20 after 1 now, and for everyone watching online, I'm going to go ahead and preview the schedule again. Here at 1:30, Rob is going to go through a walkthrough of the propeller component. A lot of you may be really interested in how this thing works and really want to see some of the useful capabilities on this, so please tune in right at 1:30 when we begin that talk. That talk is going to conclude session 1.1 here. And reminder to everyone watching online, if you click show more underneath the video in the browser, it's going to drop down and show the links to all the different sessions, or you can go to the VSP main page for the workshop and follow them there. But if you want to quickly go from one session to another, underneath the viewer itself, or the video player itself, is the link to the various sessions. So you can jump straight into session 1.2, and we will transition the stream over to session 1.2 at 2 o'clock. Where we'll begin with Rob's discussion of fit model. So with that, we're going to go ahead and mute everything and go into standby for a few minutes, get some coffee, stretch our legs, take a breather for a minute, let everybody relax their voices somewhat, and then we'll go ahead and come back and get rolling right at 1:30. All right. Well, welcome back, everybody. It's 1:30. We're going to go ahead and get started with Rob's talk to wrap out session 1.1. And then after this, we're going to move on to the second session in the afternoon. Again, as a quick reminder, everybody try and remember to set your quality to 1080p in your player so you can see things nice and crisply. And then if you look down in the description below the player, you'll find the links to session 1.2, and you can go straight there after this talk. So, Rob, go ahead. We're ready for you.
Thanks a lot, Brandon. This is mostly a set of slides. We'll see if there's time for some demo at the end about the propeller component. The propeller was added a while ago to capture the design intent in the way that people who design and work with propellers all the time work. This component can also be used for a rotor on a helicopter or a VTOL vehicle, although most of the parameters and most things are set up really from the perspective of a propeller. And if you are designing fully articulated helicopter rotors, then you're going to find the description of the hub perhaps lacking, and we don't really have that kind of articulation represented in here. So it's mostly for propellers, but can obviously be used for rotors as needed. Like every component, the propeller starts off with the design tab, where there's control of the mode that the prop is shown in, then some general design parameters, some of which are explanatory, some of which I'll detail, and then actually an output section where we talk about some of the propeller metrics that are calculated on the fly for your model. To start with, the propeller mode up at the top, you get three choices. You can either show it a propeller as blades, as both, or as a disc. And you'll notice here with the X57 model, we're showing all of these propellers as blades, where we're rendering and modeling every blade individually. On the far right, we're ignoring the blades, we're dropping them, and we're just showing an actuator disc. So we have the diameter and position represented in orientation. And that shows the arc of movement for each of those props. And then in both mode, we draw both the disc and the blades. If you use disc only mode, then your updates and your refreshes are going to be much, much faster. So I certainly recommend, if you're in a model and you have a complex combination of rotors and not rotors, you'll probably want to leave it in disc mode most of the time and only switch it to blade when you need that. Now, this isn't just about visualization. This representation mode also determines what goes to any sort of analysis or export. So when you export the geometry, if only the blades are being shown, then the disk is not going to be exported to that geometry and is not going to be communicated to that analysis. Likewise, if you're in actuator disk mode only, then the blades are not going to go to that geometry. They're not going to end up in the CAD file. They're not going to go to that analysis. And in both, then both are going to go to whatever analysis or whatever export file. So just know that what you see on screen is what you're going to get in your analysis or in your export. Now, I'm going to skip diameter and number of blades and the rotation because I think that those are pretty obvious and self-explanatory. There is some need to talk about what's going on with beta 3.4 and feather angle. And what we have here is in practice, many propellers, when they talk about, when they talk about a pitch setting, especially when it's reported back to a pilot's interface or an operating handbook, they'll talk about the angle of the pitch on a variable pitch prop at this point in time at the 3/4 radius location at 75% of R over R. And so that's what we're talking about when we say beta 3.4. That's the beta angle, that's the pitch angle at 3/4 of the blade. And this is different from just the angle at 3/4 of the blade, because later on when we talk about the twist distribution, you'll see that this blade, which starts at 20% at the root of the R over R and goes out to the tip at 1, it varies in angle from about, let's call it 47 degrees down to about 13 degrees, and along this curve such that at 75% of the blade, we're at 20 degrees. And so the twist angle varies out along the blade, and you'll notice never on this curve does it go to 0. So this is very common for a propeller, a way of specifying a prop, in that its twist is in some nominal case, say a cruise situation. It never crosses 0, but the reference point that's commonly used is this 3/4 location. So in this case, this prop, its twist distribution is 20 degrees at 75% of the blade. And so the mathematical relationship is just beta 3/4 is equal to the twist at 75%, 3/4 plus the feather angle. So if you want to specify the twist angle, the beta, the feathering of your blade in terms of beta 3/4, click this yellow button and then dial it in. We will do the math to calculate the required rotation to put the blade in that position. If you would rather work in an absolute sense and not do this math and just rotate the blade about some basal coordinate system, then just click the feather button and choose this yellow button. It'll turn off beta 34. It'll switch it to feather mode, and then it'll rotate that. Either way, the opposite value will be calculated on the fly. So if you're in feather mode, the beta 3/4 will be calculated on the fly, and likewise, if you're in beta mode, the feather angle will be calculated on the fly and reported in this box. The next option down the list is pre-cone. This is sort of a side view of a prop here on the left. I've tried to come and show the disc and the blades, but we're almost looking down across the plane of the disc. And you can see that with 0 pre-cone, the blades are in the plane of the disc. But then with 10 degrees pre-cone, they're coning forward. They're being pulled forward in the thrust direction. And they're rotating about the rotation axis, and they cone forward just at 10 degrees. And pre-cone can be in both props and rotors as a standard deflection, a simple deflection that we have. Next on the list is the construction line specified in X/C. And the default is 0.5, which is this middle case. And you can see that with this kind of a curved chord distribution, but with a X/C construct X/C of 0.5, you get a straight mid-chord line. Whereas if you change it to 1.0, then these blades are going to be straight about the trailing edge, or 0.0, they're actually straight about the leading edge. And so the construction X/C is the straight line about which the planform is developed. So when you twist a blade, or you talk about your chord being developed, these things are all done about the construction X/C line. We then have some control over the location of the feather axis. We have two options, feather axis and feather offset. Looking at a top view of a rotor or a front view here, you'll see that with axis of 0.5 and offset of 0, puts that rotation axis right down the middle of the blade with no offset. The feather axis goes right through the center of rotation. You can shift the blades about that axis, so the offset stays 0, so the rotation axis still comes to the center of rotation, but the blade shift so that at 0.25, they're now rotating about the quarter chord of each blade. Or you can use these in offsetting ways to create a result like at the bottom. So together, these control the location of the feather axis on the blade through axis, and the location relative to the rotation axis, the offset. Here down at the bottom, we actually calculate some outputs. And in VSP, you'll notice there's sometimes these kinds of boxes with a slightly blue background. And these are things that are output. They're calculated on the fly, but they're actually available as parms. So you can use them in linking. You can access them through the API. You can do that kind of a thing with them. We'll talk some more about that later. But in this case, there's lots of things that propeller and rotor people use to talk about their props and their rotors. And we just calculate those on the fly based on the geometry as a courtesy. So for propellers, they often work in terms of activity factor, which is sort of like a version of aspect ratio, and also integrated design lift coefficient. So activity factor and CLI are calculated there. Activity factor, you have to specify where the hub is in terms of where you begin your integral. And so that's what this R0 parameter does. The typical definitions are either 15 or 20% of the blade R over R. And the default there is 20%. If you're a rotor person, then you often work in terms of the average chord or the solidity, and you may work in terms of the geometric average, the thrust-weighted average, or the power-weighted average. And so the power-weighted chord, thrust-weighted chord, and solidity are all output here in these boxes. And this is always up to date with the rest of the geometry of your model. And this is a per blade chord and a per blade solidity, I believe. I'd have to double check that. We might multiply them by 3, but I'll double check that. One of the really cool things about the prop component is that unlike the wing, where you work in terms of a section from root to tip, you instead are specifying smooth continuous curves of the different planform parameters. And so things like your chord is determined by a smooth curve from root to tip. Your T over C is a smooth curve, your twist angle is a smooth curve, and you're even to the point of your design integrated lift coefficient, CLI, is a smooth curve. And then you can control these curves in many, many ways. There is some limitation. The CLI can only be used for airfoil types that we have analytical definitions of, and we can really only use it when in a span of the prop where the blade is bounded by the same airfoil type. So the rule that comes out of this is for a propeller, you really want to use as few exec types as possible, and you want to specify them in as few locations as possible. So ideally, only 2, one at the root and one at the tip. Sometimes there's reasons to go to 3, maybe even 4. The only exception to this is if you're using file airfoils, but I'd really recommend you don't do that on props because there's so much power that comes out of being able to do this as it is. There's a lot going on for the blade curve control, but you come to the blade tab. Up at the top, there's a selector for which curve you're going to be working on. Right now it's showing chord. And then there's a control for the type. Is it a linear interpolation or cubic? And we'll talk more about that. Then we have a nice big window for the interactive curve editor where you can actually drag and drop the control points around to control that shape. You have some options for splitting a curve to basically insert more control points without changing the shape, so that if you want to do local refinement, you can do that. Or likewise, you can delete control points. If there's too many specified, then you can go through and you can thin the crop. Down at the bottom, there's a fairly complex looking GUI. It's actually simple in practice for editing the control points, where you can go through and you can, if you don't want to just drag and drop imprecisely, but you want to very precisely control the numeric values of control points, you can type those values in there. And over at the very right of that, there's an option where you can enforce continuity on some of these types, so that if you know you want a particular control point to be smooth, you can click that G1 button to force it to be smooth. Now, the different planform curves, there's a lot of curves that you can edit. Chord, twist, rake, skew, sweep, axial, tangential, thickness, and CLI. So there's a lot going on here. All of them that reflect the planform are, again, this is out the distribution of a blade. They're described here in this chart. So the gray reference axes show that this is a blade section somewhere out the blade, say at the middle of the blade at 0.5. This shows the direction of rotation for the blade, and this direction is the general direction of thrust. To give that reference, twist is measured positive up from rotation. So this airfoil is shown twisted up about 20-some degrees. In this sense, the chord is the obvious definition. It's the distance from the leading edge to the trailing edge of the blade. The axial direction is in the direction opposite thrust. Rake and tangential is in the direction opposite rotation. And axial tangential are a pair that are orthogonal to one another. Sometimes propellers are instead described in terms of rake and skew. And so rake and skew are very similar to axial and tangential, but instead of being sort of aligned with the thrust and rotation directions, they're actually aligned with the chord and normal to the chord. So rake is normal to the chord, moving in a down direction, and skew is parallel to the chord. And you'll particularly find that certainly in marine propellers, they're described almost entirely in terms of that propeller having rake and skew, whereas some other tools will use the axial and tangential directions. We also have sweep, which is very similar to tangential, but instead of being specified as a fraction of the radius, as a linear dimension, it's an angular deflection. And so we have sweep as an angle that stays in the plane. It stays in this rotation disk. And we'll talk a little bit more about how it's different from tangential in another slide. My general recommendation is to avoid using redundant controls. If you're going to use axial and tangential, then you probably want to avoid rake and skew and just set them to 0 and entirely use axial and tangential. On the other hand, if you're the kind of person who likes to use rake and skew, then use rake and skew, but then don't use axial and tangential. Mathematically, VSP will let you use both of them, but you're just going to get really, really confused. So I recommend you use one, not both. This section, again, it's a sectional view from root to tip. A little bit more on the difference between sweep and skew and rotation. Here we're looking from the rear, we're looking forward, so we're behind a prop looking forward. This is a default prop that rotates clockwise. In this case, sweep is going to move this section. If you sweep the tip section, it's going to move it along the arc of rotation, right? It's opposite the direction of rotation for positive sweep, but it's going to sweep that back. And what you're going to find is that, of course, the real developed disk and the actual radius will not change with sweep. That'll stay the same. However, both skew and tangential are more of a shear, and they translate this section in this vertical, what here's drawn as vertical direction. And so they will actually change the true diameter of the blades. And we don't update the disk and we don't update the diameter parameter, but they will change the actual real diameter of the blade. So be careful with that. You can get yourself into a little bit of trouble with extreme values of skew and tangential. In a similar manner, rake and axial actually move the blade section in a linear way, like skew and tangential. In this case, it would be in and out of the plane of the screen. They don't change the diameter because the diameter is still of the projected disk, but they do change the blade length. You have the ability to control the curve type up here. And if you click the pull-down menu, you'll see 4 choices: linear, P-chip, cubic Bezier, and approximate cubic Bezier. And there's reasons to use all of these. First, linear, it's extremely simple. And obviously, and it's the perfect thing you want to do if you just want to do linear taper or linear twist, certainly as a starting point for design. Just specify the start and end point and go with linear. P-chip is a piecewise cubic Hermite interpolating polynomial, and it's this nice smooth curve. When you do a BEM file import, which I'll talk about in a little bit, that's the default. It reads in all of your points along the blade, and it fits a P-chip to them. It's a little non-intuitive making changes to a P-chip. If you've got many control points in a P-chip and you go to click and drag on one of the intermediate control points, you can get some ringing and some non-intuitive behavior. So that's not the one I like the most. Cubic Bezier, on the other hand, is the most intuitive when you have smooth curves. This is what's shown here at the right, where you have a central control point and then you're controlling the slope to the left and the right. And you can get a very intuitive, very smooth control with just a very small number of control points. So that's the one I recommend if you have a smooth distribution. There's this option to do an approximate cubic Bezier, and what this does is it takes whatever you have, which could be a cubic Bezier with many, many control points, or it could be a P-chip with many, many control points. And first, you choose approximate cubic Bezier from the pull-down, and then you click the button, convert to. So you go 1, 2. When you click the convert the button, what it's going to do is it's going to approximate your curve with a cubic Bezier with fewer control points, and then it's going to change that mode to a cubic Bezier. So this is a great thing to use after you do a BEM import and you've got just sometimes a ridiculous number of control points and your model's really, really slow. You do this approximate cubic Bezier and it's going to be better. Curve editing in general in this drag and drop area, it's pretty intuitive. One really cool thing is the model does not update until you release the control point. So if you grab this green dot or you grab this black dot, you can move it around and you see what's going to happen to the distribution on this screen, and it doesn't update the whole model until you let go. If you want to split a curve, you use this row. You can either dial in where you want to split it in terms of R over R, or you can do it with a click to pick, where you click this split pick button, and then the next place you click, it'll split it nearest the mouse point. So you can just click to split. And likewise for deleting, you can either choose by index, you can roll through this and the little yellow box will move and tell you which point. And then when you delete, and you hit this delete button, it'll obviously delete it. Or if you want to click to delete, you can click the del pick and then the next one you click on, it'll delete. Down here at the bottom, you can adjust all these things precisely with just a regular input that like any other VSP component. And things that you can't change due to the math and whatever's being done will always be grayed out. So things you can't change will be grayed out. Things you can are white and bright. And if you want to set that G1 continuity, click the box and some other things will gray out. On the XSec tab, it's almost identical to that for a wing, so I'm not going to spend too much time on it. There are a couple of tricks. If you want to change the hub cutout, the root section of a prop blade, the way you do that is you come to the 0th X section and you change its radius. So you change the 0th section R over R to change that hub cutout. That one's tricky. People miss that one a lot. In general here, you want to use as few as possible. I'm very strict on this. Ideally, 2, and 2 is sufficient in almost all circumstances. And you're going to use that if you have a prop with blades all of the same family. 3 is what I would go to if I had a circular cuff for a variable pitch blade or maybe an elliptical cuff that then transitions to a single blade type all the way out. And maybe 4 if I knew that the root section was one blade type and the tip was another, and then there was a distinct area in between where things were transitioning. So there's really, again, as few as possible. Don't go crazy here because it doesn't make sense in a prop. A couple of exceptions. If you're using file airfoils or CST airfoils, you could use more, but both of these are kind of clunky and awkward with the propeller. It's not ideal. And so for a prop, I really recommend you use the analytical types and you use as few of them as possible. The modify tab is identical to the wing modify controls. It allows you to tweak things up here at the top, and you generally won't use this for a prop, the shift rotate scale. If you do want to blunt a trailing edge or modify the trailing edge to be rounded or something like that, these things work. And what you'll find is it should be really smart in that if you specify a blunted trailing edge of a 1/4 inch thickness or 1 centimeter thickness at the root and at the tip as dimensional thicknesses, even though the chords are different and vary along the blade, it should figure that out and keep a constant thickness all along. So it generally should do what you want it to do in that case. The More tab includes folding control as well as tip treatment. The folding control allows you to put in a folding prop where it can either fold like a model airplane propeller that goes back along the body. It can fold like a STEME S10 motoglider that folds in the plane of rotation, or you can do a complex fold like the folding props that Brandon designed on the X57. You get to set the folding axis, both its position and its direction. So a vector and a location, as well as the angle, and all those are set with these parameters up here at the top. I do want to point out there's a couple of icons on a prop that you may or may not have noticed. At the center of a prop, there's a vector showing the thrust direction, and as well as the rotation direction for positive rotation. Similarly, for the fold axis, there's a line showing the fold axis and the direction for where that fold is. So as you change these fold parameters, this icon will move around to show you where it's going to fold about. Below that, the tip treatment is identical to the way a wing treatment is controlled in terms of rounded or flat tips. So that should be very familiar. And likewise, the tessellation control for clustering should be very familiar. Clustering is controlled over an entire prop. It's not section by section. It's the entire thing at once, which is generally pretty nice. The resolution itself is on the general tab. On the gen tab, the num-u and num-w control that overall tessellation resolution on a prop. Propellers have the neat ability to do a boundary element method style file for both import and export. It's not in a format that exactly goes into any particular BEM code. The idea is that this file just contains the information that a BEM code would need in a very simple file format to work with. So you should be able to convert it to whatever your favorite BEM is, whether it's something you've implemented in MATLAB or whether you're using Xrotor or QProp or OpenVMT or whether you're just doing a spreadsheet. The way you get to it is you go to the File menu and then you click Export. You then, I don't know why this says identical to similar wing controls because that's nonsense. But you go to Export, the Export menu pops up, you choose Blade Element, and that'll pop up. And if you have multiple props, you choose which prop you want to export. So 1, 2, 3, you say, okay, there'll be a file display, you give it a name, and you move on. And it'll dump out a file that looks approximately like this as a BEM file. There's some information up at the top that's just sort of general information about a BEM file. The number of sections is determined by num-u. Then it's going to have a table where it specifies all of the blade planform curves at that num-u, so in this case 66 points. And then after that, it's going to dump out the airfoil coordinates at all 66 stations. So whatever those airfoils that get developed and get interpolated are, they're going to get dumped out here. So that's a big long file. We can not only export that file, we can also import a BEM file. Again, you go to File, Import, choose the blade element, a file chooser, you choose the file and you import it. There's a couple of notes here. When you import that file, we're going to ignore those airfoil coordinates, those airfoil ordinates. So if you're making your own, say you're writing a BEM file in MATLAB or in your spreadsheet, you just come down to here and you stop before the airfoils. There's no point in going further. And that'll read in your blade plan form and get you a nice blade to start with. All the curves from that distribution are set up with p-chip and a point at each station. So in this case, if there were 66 lines, that's way too many. You don't want that many on import. You would have 66 points in every single one of these curves, and they would all be p-chip. That's why I recommend after you import from a BEM file, you use the approximate cubic Bezier to simplify those curves and get rid of a lot of those redundant points. So it will be very overdefined when you import it. It will be slow until you clean it up. If you have 66 points on all of those curves, it's going to be ridiculously slow. Even after you clean it up, propeller is slow. It's a complicated component, I know that. But definitely don't shoot yourself in the foot with an overdefined thing. And I believe that's the last of it. And we're basically down to the final minute. So I'll try and answer some questions through chat, but I don't think that we're going to have time for a live demo.
Yeah, thanks a lot, Rob. I mean, we've had a couple of comments in the chat, but for the most part, it seems like that covered quite a lot of material and explained quite a bit. So I know we have you scheduled for some back-to-back talks here. So if you like, here when we switch over to session 1.2 for the afternoon and switch the streams over, if you want to give the talk and shorten that to whatever length you feel appropriate, and then if you like, I will walk through that traditional pod example where we do fit model using that geometry. That way you don't have to talk for that whole half hour and you can give yourself a break. If you like, you can run the show. That's entirely up to you.
I may take you up on that, Brandon.
All right. Well, we're here at 2 o'clock. Everyone online, I'm going to go ahead and end the stream for session 1.1. Please remember that you can click on Show More and find links to all the different sessions below that. We can jump over to session 1.2, where we will begin the new stream and start with the afternoon session. So everyone, if you want to follow along, please go ahead and jump over to that session and the stream will start, and we'll start with those presentations here in just a moment. So thank you very much, and we'll see you on the other one.